Ready to start our conference dedicated to close wide wave binaries, and it is my pleasure, my honor, to present the President of Republic of Armenia to open this conference. I hope he will explain how he come to be interested in this conference. Thank you very much, Mr. President.
Well, good morning, everybody. First of all, my apologies, I'm not properly dressed. I look at you, at your freedom, the way you are dressed, and I remember the wonderful days that I was also in science. Sometimes I think that the most exciting and relaxing and fulfilling time of my life when I was like you doing my scientific work. And of course I was very concerned those days, concerned what I was doing. As a theoretical physicist, I was doing research in two directions. Initially, it was first a relativistic astrophysics, more or less doing what you are doing, but from the theoretical point of view, looking at neutron stars, compact objects, and trying to explain them, how on earth you can have on that sort of a small scale that huge power or mass or energy, and how do they interact. And the second one, looking at theory of relativity. I'm not sure that do you know a theory that the last days of his life, Albert Einstein with Nathan Rosen were developing the biometric theory of gravitation. So I was doing several works on that. That it went into more detailed work, which was mathematical modeling of complex system. And the first complex system for me was a neutron star. It was a complex system. But you will laugh again when I'll tell you that I tried later to do mathematical modeling of other objects, some of them human objects. And it appeared that these objects are even more complex and unpredictable, especially now. So as a result of that, I came to some ideas how to implement those, the mathematics theory and the experience that I had in theoretical physics into applied science, like the science of human behavior. It ended up with several papers that were not published, but recently, probably in end of this year or beginning of the next, a book will appear. Because I was told it has value, and the title of the book is The Quantum Behavior Global Risks and the Basics of Quantum Politics. So that explains you, first of all, probably why I'm here. I am here to go to my base, to my sources, base, and happy days. Enjoy your freedom. Enjoy what you are doing. Let the structure of a neutron star or of a binary star be your biggest problem in your life. Not the problem of politics, economy, and other things. So, second, I would like to congratulate the organizers, Dr. Tovmassian, Mirzoyan, and others, that are doing this for science, are doing this for humanity, but also for Armenia. But it's very important for Armenia to continue being a scientific research center. Because I do believe that we are on a crossroad of a change, because 21st century is going to be completely different than we had in 20th century, and that main change will be the conversion of science, technology, human behavior, including politics. And of course that starts for simple gadgets, the technological advantages that we have, and it will have huge impact on many things, including the basic social behavior values and theories that we have. Because if you take one of the basic ideas, which is democracy, I think we all lived, especially in Europe and in America, in Eurasia, with the basic ideas of democracy where people delegate their power, and let's say the parliament or the president have the 5 years of running the country on that mandate. I think we are living in a world that it's not 5 years, it's every day. Your Facebooks, Twitters, and so on and so forth. So people are changing. Democracy is changing, technology is changing, political leaders are changing. Some of them have quantum behavior, using the same gadgets, be it the Facebooks or Twitters. So this is the new world. And of course, my vision or a hope for Armenia is to become another hub. Because in 21st century, I do believe that the strength will be not only how much gold or oil you have. It will be, I think the real value will be the human brain and the human creativity and what you can create using your experience, your science, your technology, because it's already today, the biggest world companies are not ExxonMobils or BPs. The biggest world companies are the ones that we know, starting from Microsoft, going up to Google and Facebook and others. So the world is changing, and I'm sure it will change dramatically when the new tools will appear in astronomy. I was 1.5 months ago, I was in Canary. Didn't go for a holiday, went to see the observatory, and I went to see also the future of the astronomy there with a scalable, huge telescope that they are planning to do, and not only there, but 3-4 months ago when I was in Germany, I visited the Munich, the technological university, and the astronomical center. It's very exciting. And I would love Armenia to be on the crossroad, and I would love Armenia to be a home for you. So welcome to Armenia. I hope you will enjoy here. Not only Armenia, but enjoy your discussions and what you will learn. Because you are here also not only to present, but also to learn. That's the natural process. I wish I'd had the time to sit and learn from you. But unfortunately, I have to tell that this doesn't allow me to do it. So I wish you all the success, Dr. Tovmassian, colleagues, and I hope to see you again. And I hope one day, after my retirement, I will join you as a free scientist. Thank you very much. Bye-bye.
Thank you, Mr. President.
Thanks. Okay, right, so thank you very much to the organizers for inviting me to talk to you about white dwarf binaries. So I'm also going to focus on properties of double white dwarfs from theory, because that's what I'm more familiar with. But I'll try to make some inferences of what we can potentially learn about actual observations of these systems, because we do expect a plethora of phenomena to occur from white dwarfs, both merging and just simply interacting through Roche lobe overflow and mass transfer. So I came from Australia, so I'm based at the University of New South Wales in Canberra, which is actually not in New South Wales. So Canberra is the capital of Australia, right there. I originally moved to Australia 5 years ago to work as a postdoc with Brian Schmidt at the Australian National University, off to the sort of in the western part. And just almost a couple years ago, I moved across to the other side, east side of Canberra at University of New South Wales. And so we have quite a small astronomy group. We're trying to build our group right now. We're mostly focused on understanding progenitors of type 1a supernovae and other transient phenomena, supernova remnants, etc. And so we are looking for PhD students. So I'll throw up at the end of my, not throw up at the end of my talk, but at the end of my talk, I will put up a slide relevant for this to anyone who might be interested or know students who might be interested to pursue a PhD study down under. Okay, so for double white dwarfs, we know, based on binary population synthesis calculations, mine as well as other people's, that there are over 10 to the 8 double white dwarfs predicted to exist currently in our own Milky Way. We know most of these are, most of these probably will not actually be detectable, either electromagnetically or even with gravitational waves, because their orbital periods are simply too wide to see them. But there is a substantial fraction of these that we hope with future space-based gravitational wave observatories like LISA, we'll actually be able to resolve physical properties of these binaries and better understand the evolutionary processes and the evolutionary channels that lead to the formation of these different, of these white dwarf binaries of different composition. So we expect a lot of interesting phenomena to obviously occur through interacting double white dwarfs, from CVs like AMCVN type systems, which are important for gravitational waves. And I know we'll have some talks about AMCVNs during this meeting, which I'm very much looking forward to hearing, as well as formation of our Coronæ Borealis variable stars, and of course type 1a supernovae events. So this slide has quite a lot of text, but I just kind of wanted to go through many of the transient events we could expect to occur from different interacting double white dwarfs. So on the left-hand side, I have non-merging systems, and on the right, showing what merging white dwarfs might do. And I sort of broke them down according to mass. So maybe you can't distinguish very well from the blue and the green, but the bluish sort of areas represent white dwarfs that are of low mass. So typically helium white dwarfs that are only formed in binary evolution when you, say, strip a red giant of its hydrogen envelope. And then the green in sort of the mid-range mass of white dwarfs, and then the orange, the more heavy systems that are more rare. So we can expect things like helium novae, like V445 PUP, AMCVN systems, of course, which, you know, I think a decade or so ago it was thought these are double white dwarfs, but I think it's becoming more apparent that while likely maybe that donor is not actually degenerate, but a helium burning star, a low-mass helium burning star that's been stripped of its hydrogen. Another, you know, non-merging white dwarfs you might expect to find type 1a supernovae. And so here, I'm going to talk about type 1as a little bit more in the talk. I know we have a whole day, Thursday will be dedicated to type 1as, but I can't help but throw some slides in there on type 1as since it's what I typically work on. We could expect sub-Chandrasekhar mass type 1as to arise from CO, or carbon-oxygen white dwarfs accreting from, in this case, say another white dwarf that's helium-rich. And then, of course, as you go to heavier white dwarfs, we may expect other types of systems, plausibly these type 1ax supernovae, although those generally have very young ages or short delay times. They probably do not involve a donor that's a white dwarf star. But we very well may expect to find neutron stars formed via accretion-induced collapse through interacting systems in Roche-Loeb overflow. And then conversely, sort of analogously, we have the merging white dwarf systems, in which we also would expect a range of different objects to be created, including the sub-dwarf B stars, our Coronæ Borealis variable stars, of which we know about 150 of them on our own Milky Way. I think a few years ago we only knew maybe 40 or so. Then, of course, the type 1a supernovae, we think we can also make these through mergers. In fact, this might be the dominant channel that make 1as. There's also a subclass of type 1a supernovae called 1991 BG likes. And these are more, basically they're fainter than the so-called normal type 1as that make up about 70%. The 91 BGs are fainter, a bit harder to observe, but they're known to be associated with old stars. Whereas regular or normal type 1a supernovae, we find them amongst all different types of galaxies with different stellar population ages. And analogous to type 1as we might make from double white dwarf mergers, if you have two oxygen neon white dwarfs, for example, merging, you could expect to make a neutron star from that merger. I'll talk more about these things in some more detail later. So a little bit about our Coronæ Borealis stars. These are very dusty, hydrogen-poor, yellow supergiants. They're thought to be mergers of white dwarfs, probably a carbon-oxygen-rich white dwarf and a helium white dwarf. It's not completely clear. Essentially, shown here is a light curve of one of these. I know the axes are probably difficult to read, but this is showing how the light curve of an R-core star over about a 10-year span varies by about 9 magnitudes. And the reason for the variation in the luminosity of these objects is thought to be caused by clouds being ejected. Okay, so basically you have this formation scenario where you have white dwarfs merging. They don't explode, but they make this R-core star, and this phase lasts on the order of 10 to the 5 years. And when a cloud of dust is emitted toward our line of sight, we see these intense drops in luminosity, and that's what's thought to be the cause of the variation in these stars. So I'm part of a program led by Mike Bessel at ANU, who's the PI, and Patrick Tisserand in Paris is the lead observer on this project, where we're carrying out spectroscopic follow-up of R-core candidates. And so it's really important to try to, well, I think it's important to try to figure out what the progenitors of these things are, because it's sort of an interesting low mass analogy to what we might expect make type 1a supernovae through mergers. So we expect a lot of type 1a's come from mergers of white dwarfs, probably 2 carbon-oxygen white dwarfs, but that's still up for debate a little bit. These are kind of seen like a low mass analogy, so it'd be interesting to figure out where that sort of barrier lies between when you make an R-core bohr and where you might make a thermonuclear explosion. So here's a typical formation channel from some binary population synthesis code from Star Trek simulations that I found were typical of what you'd expect leading to an R-core bohr star. You basically have one main phase of Rochelab overflow where you have stable mass transfer to a main sequence star from a giant. You first form a helium white dwarf. So this is just showing one channel. You could have scenarios where you form the CO white dwarf first. I'm just showing one example. Later on, you have an unstable phase of mass transfer, or a common envelope event, which happens on the AGB. Eventually, that second star that lost its envelope turns into a CO white dwarf, and that helium and CO white dwarf merge. And so this is sort of one of the main channels, plausibly leading to an R-core bohr. But we found that actually, a subset of these helium-CO white dwarf mergers may be responsible for making these 91Bg supernovae that I mentioned earlier, this sort of faint type 1a's. So the reason why we basically think that, and so I don't have time right now to go into details of this paper, this Nature Astronomy paper from Crocker et al. 2017, but in that paper we basically argued, based on ages, so delay times of these mergers, we argued that a subset of these mergers of carbon, oxygen, and helium white dwarfs, instead of making R-core bohr stars, which is sort of would dominate the left side of this delay time distribution plot, this just shows you when you would get a merger as a function of time, assuming you have a starburst at t equals 0, so that's just the delay time distribution. Some fraction of these, one particular formation channel, only kicks in at really long delay times. And so in a nutshell, to sort of gloss over a lot of the details of the paper, the main point is we found that in order to explain a particular observational feature of our Milky Way, okay, that happens to be the annihilation signal observed from positrons annihilating in the Milky Way. This is a 40-decade-old problem. Something of stellar origin that has a relatively long delay time, so basically waits a couple gigayears after star formation until it starts to take off. We need something like that to be able to explain this antimatter signal. And we found that these mergers, the specific channel of helium-CO white dwarf mergers, fit this bill. And we propose that these are likely a progenitor for these 91Bgs. They cannot be progenitors of normal 1As because the mass of these mergers isn't enough that you could create the right amount of nickel-56 to make these things bright enough. Because basically, type 1a supernovae typically create half or more than half of a solar mass of nickel-56. And it's the radioactive decay of that nickel-56 that powers that supernova light curve. And so you need to have enough mass. These things are a bit lower mass. They produce some nickel, but not a lot. So it's a pretty good story overall. There's still a bit of uncertainty as to how the explosion would actually proceed in these low mass mergers. So that's something we're basically working on. But this is something that we proposed a couple of years ago. So I'm going to just now start by showing some distribution plots, showing total mass of mergers of various types of white dwarfs through binary population models. So I'm only showing distributions for one particular realization of models. So in binary population synthesis, right, so we essentially start out with an assumed distribution of eccentricities and masses and initial separations for a wide range of binaries. So for example, I'm running now the code on supercomputers. I can evolve 12 million binaries for one model in 24 hours. So you end up with pretty good statistics, and you can then characterize, okay, what are the final properties of whatever I want to look at. So in this case, it's helium and CO white dwarf mergers. You might want to look at neutron star mergers, things like this. Of course, you have to make some assumptions for the binary evolution physics, which you don't have to worry about with single stars. So you need to make some parameterizations for what happens when the star goes through a common envelope phase, which every closed binary has to go through at least one of these things. So this is just sort of for one particular model realization, and if you have questions about that model, I'm happy to answer them. So this is showing on the x-axis the total merger mass when you merge two white dwarfs together. So in orange, there's a helium plus a CO white dwarf, and well, you might think it's the same thing. In blue, there's a CO plus helium white dwarf. I'm actually showing you the different channels because you can see that they have slightly different mass distributions depending on exactly which formation channel you're talking about. They all have kind of a peak. They peak around total mass of around 0.9, sort of typical of what you would expect from R-core Bohr stars. But you have a few different evolutionary pathways going on there, depending on when you have the common envelope and so on. If I include white dwarfs that have, in green, that have a CO white dwarf merging with a so-called hybrid helium-CO white dwarf. So these HeCO, sorry, I keep pretending I have a laser pointer, but yeah. These are sort of, these hybrids have basically a carbon-oxygen rich core with a helium-rich sort of outer layer. They're basically failed CO white dwarfs, only made through binary evolution. They cover a slightly more massive sort of range than the other two. I can do the same thing for the flipped channel of that. I don't have any CO-CO mergers on here, just talking about sort of the lower mass end. In purple now, I've plotted the mergers of two helium white dwarfs, which interestingly have a total mass peak at around 0.5 solar masses at time of merger, and some other weird things happening here. It's known from observations that subdwarf O stars, right, so these are spectral type O, not on the main sequence, small stars, have a mass of around 0.5, so this fits really well with what we get from binary population synthesis models for the total mass. So it seems plausible that these SDO stars are very well formed from the merging of two helium white dwarfs. Let's see, yeah, so the R-core Bohr stars are known from observations to have masses of around 0.8 or 0.7 to 0.9, something like this, which follows around in that range there. So you have a combination of potential different pathways that could make R-core Bohrs. The 91Bg-like supernovae, like I was mentioning before, if they come from a similar formation channel of R-core Bohrs, but basically a sub-channel of this, but we need to have them a little bit more massive, otherwise we don't quite make the nickel 56 that you need to at least make some of this for it to be considered a type 1a. We find that, you know, it sort of works out that these say on the, yeah, this sort of orange, there's a peak in the orange distribution there that correspond very well to these properties that we might expect for 91Bgs. So those again coming from helium white dwarfs merging with a CO white dwarf. And then there's, of course, other things, hydrogen-deficient stars and other objects. So this is now showing the exact same channels I just talked about, but only their delay time distributions. So previously I showed the total mass at merger. This shows when you expect them to form after, say, a star formation burst at t = 0. And you can see again the orange sort of histogram, which I'm saying, okay, maybe these are the 91Bgs. They do kick in at slightly later delay times than their counterparts that come from very similar formation channels involving a helium and a CO white dwarf. There's also something that's been talked about for the last few years. It's gaining popularity, these calcium strong or calcium rich. Calcium strong is probably the better term, gap transients. And for a while it was like people were just wondering, what are these? Are they core collapse supernovae? Are they thermonuclear? And I think it's pretty clear we think these are probably some kind of thermonuclear explosion, and most likely something involving white dwarf mergers. And there was a recent paper by Shen et al. On AstroPH that suggested that maybe these things come from the merger of oxygen neon white dwarfs and helium white dwarfs. Now in population synthesis studies, you don't find these at all. So just the evolution doesn't work out in plain field evolution. You need some sort of dynamics. So if you have something like a three-body interaction, say in a triple or in the centers of globular clusters, something like that, you can plausibly harden the helium white dwarf oxygen neon binary, because we do make them, they just aren't close enough to merge. And somehow those get kicked out of the cluster or out of the triple, and we actually see these calcium strong transients happening fairly far from any host galaxy in most cases. So this is a kind of really interesting potential formation channel for these objects, but again, this is a new idea and still needs a bit of investigation. Okay, so I'm going to talk more about type 1As, just a few slides. Don't want to talk too much about it because we have Thursday to look forward to those talks. So historically, basically, white dwarf mergers, they were not expected to actually produce type 1As through merging two CO white dwarfs. There were, Webbink and Eben and Chudakov have well-renowned papers from the 80s stating that, oh, you could make type 1As through this channel, maybe, and actually Ron Webbink also proposed you can make R-core bores through the helium and CO mergers. That paper had a lot of information and complicated plot in there, but yeah, really great work. But it was thought that you're more likely, through theoretical simulations up until sort of 10 years ago, showed that if you merge two CO white dwarfs, you're more likely to actually form a neutron star through accretion-induced collapse, or I like to call it merger-induced collapse in this case. Now the reason why, essentially, you would do this, it was thought, because when you have two CO white dwarfs merging, you have the more massive one sitting there, and the less massive larger one gets disrupted onto the more massive one and accretes onto it. And during that accretion process, you basically ignite carbon off-center. So that carbon burns to heavier products, like oxygen and neon, and you basically turn that white dwarf that's accreting the secondary into an oxygen-neon-rich white dwarf. An oxygen-neon-rich white dwarf, as it approaches the Chandrasekhar mass limit, okay, around 1.4, what happens is electron captures onto products of oxygen burning, like magnesium, end up being responsible for removing electron degeneracy pressure in that white dwarf. And so that oxygen-neon white dwarf is more likely to collapse because of electron captures than, say, a CO white dwarf, in which you're more likely to actually ignite that carbon. Okay? If you have a CO white dwarf that approaches the Chandrasekhar mass limit, at some point that central density becomes high enough that you'll ignite the carbon, not explosively at first. It takes a few centuries of convection and heat to build up before you get the thermonuclear explosion rip through that degenerate white dwarf. But in an oxygen-neon white dwarf, you may actually start burning oxygen, again, not explosively, but the oxygen ash ends up capturing electrons and you remove support. So that's why you collapse in the oxygen-neon case and you likely explode in the CO case. There was a paper about 9 years ago from Pakmar et al. That showed you could actually ignite carbon explosively in a sub-Chandrasekhar mass white dwarf during a merger. So this, just in the last sort of 9 or 10 years, there's been a real paradigm shift in what we think might be the dominant channels for making type 1a supernovae. So we used to think, at least when I did my undergrad, the textbooks would all say, oh, you get a CO white dwarf approaching the Chandrasekhar mass, and then it explodes, and the donor's a red giant or a main sequence star. And I mean, now we think, yeah, those probably, I think those happen too, but many of these supernovae could probably be explained by sub-Chandrasekhar mergers. So you have dynamical events with lower mass white dwarfs. But you need the white dwarf to have a mass of around 1 solar masses to make enough nickel to look like a normal 1A. And this just shows you the Phillips relationship in the black line, and you have all those crosses represent normal 1As that are useful for cosmology, but there are a plethora of other type 1A-like things that do not follow the relationship at all, showing that we think there are probably at least a minimum of 2 different formation channels, likely more, leading to 1A-like events. Okay, so I like to sort of categorize type 1As not so much as single degenerate and double degenerate. I prefer to use the categories more in terms of how the explosion mechanism proceeds. So in this case, it would be Chandrasekhar mass or sub-Chandrasekhar mass, because the 2 mechanisms for explosion are very different in terms of what happens in driving the explosion. So that would mean that the 2 sort of scenarios on the right are the ones that we care about in terms of double white dwarfs. You could have a situation where a sub-Chandrasekhar mass white dwarf is slowly accreting from stable Rochelab overflow from a helium white dwarf, or you have a dynamical timescale merger. Both cases are probably likely, okay, so I would say probably, to have the same explosion mechanism, which is called a double detonation. So you have enough helium, even in the merger case, you have some remnant amount of helium left over from previous evolution, from stellar evolution, to act as a catalyst where you get a first detonation in that helium layer when the merger starts, and that drives a second detonation near the core, okay? So this is kind of this double detonation scenario. You can have it sort of in the classical Rochelab overflow case, or you have a dynamical merger. I'm not saying that you cannot build up to the Chandrasekhar mass here. That's a sort of old school version, and that might very well happen. But you can make these things look like 1As even before they reach the Chandrasekhar mass. And it's probably easier. So we had a paper about 6 years ago in which we took population synthesis calculations of white dwarf mergers, looked at the primary masses of those white dwarfs that were in those mergers, because that's where the iron peak elements are made, okay? In this context, we care about, say, seeing, can we explain type 1a supernovae from double white dwarf mergers? It's sort of a really neat problem, because if you assume that in a merger, and this is pretty good assumption, though still not completely clear, if you assume that all of the iron peak elements, like all the nickel 56, is synthesized in that primary white dwarf, the more massive one, if you know the mass of the primary white dwarf, you can calculate what the peak luminosity will be, okay? The peak magnitude. And so we took masses from population synthesis. We had a bunch of hydro models, exploding sub-200 mass CO white dwarfs, ran them through radiative transfer simulations to look at their spectra and light curves, and we found, sorry, it's hard to probably see this. Can you see the gray histogram in the background? Those are sort of hard to see here, but there's a gray histogram showing the observed peak brightness distribution of local 1As, so from within 80 megaparsec. This is from Lee et al., 2011. And then the lines show the population synthesis models. Basically, we found that double white dwarf mergers can explain the peak brightness distribution as well as the general morphology of the distribution and peak brightnesses that we would expect. So this is pretty interesting. This is sort of at a time when white dwarf mergers were already gaining momentum as a likely candidate for type 1As because they have delay time distributions that look very close to what we would expect, or what we see from observations of type 1As. Okay, so I'm going to step away from the 1As now and just talk a little bit about the heavier sort of counterparts, the white dwarfs involving, or the mergers and interactions involving oxygen-neon white dwarfs. Right, so most white dwarfs that are created, most stars will end their lives as white dwarfs, actually, that are CO white dwarfs, but we do have the heavier end that will be oxygen-neon. Okay, so there was a recent paper came out this year, my paper on accretion-induced collapse in binaries, where I basically looked at rates of potential neutron stars forming in binaries, whether you have Rochdale overflow and then the oxygen-neon white dwarf reaches 200 mass, or you have a merger of two very heavy white dwarfs. So in this case, either oxygen-neon with an oxygen-neon, of course these things are rare, but they happen, or oxygen-neon and a CO white dwarf, okay? And tried to see what we can learn from that. So one interesting thing that came out of that paper, which, okay, let me explain this. One thing that LISA will be able to see when it flies in 15 years is, one of the things that LISA will be able to measure is something called the chirp mass. So it's basically related to the mass of a binary system. This equation here, sorry I didn't write it properly in LaTeX, but anyway, you get the idea. So you can plot up, for example, the chirp mass, which is measurable in gravitational waves, just as a function of number. These are from my simulations. This is like 12 million binaries for each model. The only difference between the two models, these are all mergers of heavy white dwarfs, by the way, these MICs. The only difference between the models is what I assumed for the common envelope formalism, okay? I won't go into the details of that, but it turns out that the interesting thing is you have a very different looking distribution depending on what you assume for common envelope. Now, the thing is with LISA, it probably can't see out far enough that we'll be able to have such great statistics for these heavy white dwarf mergers. However, this can also be applied to other types of white dwarfs. CO, which are a lot more common. The lower mass ones are probably harder to see with LISA, but I thought it was really cool that maybe with LISA, and by observing chirp masses, we might be able to say something about common envelope physics. So this is just one of the cool things, new things that we might be able to do with gravitational wave astronomy and learning about double white dwarfs. For those that are interested, so I just put up here some different potential rates, some sort of rough rates for various phenomena we would expect now in the Milky Way. How much time do I have? Oh, okay. Yeah, so assuming a 50% binary fraction, and I assume a constant star formation. This is why I say it's an approximate. for our purposes, it's actually pretty fine. We get roughly the right R-core Bohr, assuming an R-core Bohr lifetime of 10 to the 5 years, we get roughly the same rates from theory that we would expect from observational results, the recent results of Patrick's paper from last year, which is encouraging. Yeah, and then it turns out that, so the tables in that recent paper from this year, but the rates of AIC and MIC are both about 2 times 10 to the minus 4 per year, so a couple percent of the type 1a rate that we would expect for the Milky Way. So I'll just briefly give a synopsis of this slide because there's a lot of text. Punchline is that these lower mass sort of mergers, we think most of them probably make R-core Bohr or hydrogen deficient stars. Some small fraction could plausibly be the progenitors of faint type 1As, so in particular the 91Bgs, which are known to occur in old stellar populations. Fiona Panther has a paper that was just accepted on that. It seems that CO-CO mergers right now are still, they can explain a lot about normal type 1As. And when I say normal, again, I mean the majority, the ones that are useful for cosmology. But again, I do believe there are multiple channels of these things contributing. And one thing I didn't really talk about is that these mergers of heavy white dwarfs that make neutron stars, some of these have very long delay times. So when the donor is a white dwarf, or a main sequence or a red giant, but we're talking about double white dwarfs here, you can get very long delay times, which is interesting for plausibly explaining why there are some young pulsars observed in old globular clusters, right? You wouldn't expect to have sort of a young neutron star in an old stellar population. So this is one way where we would obviously expect to see these things in globular clusters through these formation channels. Some general open questions about AMC-VN binaries, which I think we'll hopefully learn more about during the meeting. Would be really excellent to constrain the common envelope evolution physics with LISA of double white dwarfs by looking at trip masses. And hopefully, I mean, LSST, that's going to be online soon, we can learn something more about the close population of white dwarf binaries with this. So it's still not clear. I guess for the full stack of images, we can reach an R magnitude of less than 20, 27, 28, something like that. Yeah, and I just wanted to point out that for population synthesis, one thing I want to say, because some people say, oh, population synthesis, you have all these parameters you can change and get all the rates you want. And that's not actually true. I mean, you can try, but it's actually harder than it sounds. The rate predictions for events don't usually vary too widely when you use, say, different common envelope descriptions. One thing that does change more significantly is the formation channels, right? Because you just change the parameter space where you're grabbing your binaries from. So I just wanted to make that point. And this was a slide I wanted to mention about our PhD program at UNSW Canberra. If you or anyone you know is interested, you can direct them to this page or to email me, and I'd be happy to talk about potential research projects. So thank you very much.
So, hello everyone, my name is Anna, I'm a fellow at AAVSO, and I would like to start thanking the conference organizer for inviting me and giving this talk, in which I will present some new observational results about the properties of the local CVE population as derived from Gaia DR2. So, this is the outline of my talk. I will start with a short introduction about cataclysmic variables, because I think not all of us work on CVs in this room. And then I will have a short discussion on how they evolve, and then I will finally present the first volume limited sample of CVs obtained from Gaia DR2. And thanks to this volume, we have been able to nail down several observational parameters, particularly the space density. And the results that I'm presenting today are also presented in a paper which is currently under review to MNRAS, but you can already access it through this archive link. So, what are cataclysmic variables? cataclysmic variables are compact interacting binaries, which have short orbital periods between 75 minutes and 2 days, in which you have a white dwarf that is accreting from a late-type star. And in the most common configuration, the secondary is losing mass through the inner Lagrangian point. This flow enters into the Roche lobe of the white dwarf and then forms an accretion disk and then is accreted onto the white dwarf. However, you have different possibilities accordingly to the magnetic field of the white dwarf. So in the most common case, the white dwarf is not strongly magnetized, so you have the formation of an accretion disk. However, you can also have the opposite case. You can have a white dwarf that is strongly magnetic. And in this case, the accretion flow will follow the magnetic field line, because the strong magnetic field from the white dwarf will prevent the formation of an accretion disk. And you also have an intermediate configuration where the white dwarf is magnetized, but its magnetic field is not strong enough to prevent the formation of the accretion disk. So you have an accretion disk, and its inner region will be disrupted by the magnetic field of the white dwarf. And in this inner region, the accretion will follow the magnetic field lines. But in the following, I will not focus on the difference between these two configurations, which are known as polar and intermediate polar. Oh, okay, thank you. But instead, okay, that looks already too difficult. No, don't worry. It's okay, I can walk there. It's working? Oh, okay. But instead of considering the difference between polar and intermediate polar, I will just consider CVs as split into population as non-magnetic CVs and magnetic CVs. And I would like also to spend a few minutes to talk about why these systems are important, because we shouldn't neglect CVs, as often it happens, not in this conference, but outside this field. And so these systems are numerous, are nearby, are relatively bright, and so in CVs we have direct access to all those parameters that are usually of difficult determination in other kinds of accreting systems. So we have kind of easily obtained orbital periods, we can easily measure temperature, masses, accretion rate, we can even get abundances and rotation rates. And also, we have to remember that the physics describing white dwarf and secondary stars is fairly well understood. And for all this reason, cataclysmic variables are the ideal laboratory in which we can test, constrain, and further develop our understanding of the evolution of all kinds of compact interacting binaries. And that's the reason why we should try to have an understanding of CV evolution that is as complete as possible. But how this system evolve? So the evolution of CVs, as that of all compact interacting binaries, is driven by orbital angular momentum losses. And this come mainly in the form of magnetic wind bracking, which arises from a magnetized stellar wind from the secondary, and gravitational wave radiation. So, angular momentum losses continuously shrink the system, keep the secondary in touch with its Roche lobe, and set the mass accretion rate onto the white dwarf. So we can look at the evolution of the system if we have a look on a plot where you have the mass accretion rate as a function of the orbital period. And CVs are formed at long orbital period, and then they lose angular momentum. And as they lose angular momentum, they shrink, so they evolve from long to short orbital period. And at this stage, the evolution is driven by both magnetic bracking and gravitational wave radiation. At about 3 hours, the secondary become fully convective, so it cannot sustain a magnetic wind anymore, and so magnetic bracking is greatly reduced. And what happened is that the secondary detaches from its Roche lobe, and between 2 and 3 hours, there is no mass transfer. So the system evolved as a detached binary in what is called the period gap. The evolution is still driven by the gravitational wave emission, so the system is still shrinking and still moving towards shorter orbital periods. And at about 2 hours, the Roche lobe catch up again with the secondary, and so accretion resumes. And the system starts accreting again, moving towards shorter orbital periods. However, now the evolution is driven by gravitational wave radiation, which is less efficient than magnetic bracking. And that's why you have the system below the period gap are characterized by mass accretion rates that are lower compared to the system above the period gap. And at about 70 minutes, the secondary become a brown dwarf, and becoming a brown dwarf, it stops shrinking in response to the mass loss, and consequently the system starts evolving towards longer orbital period, becoming a so-called period bouncer, because you have this kind of bounce back in the evolutionary track. And this is a general framework describing how CV evolved, and it was mainly developed in the 80s, specifically to explain the existence of the period gap and of this period minimum at about 70 minutes. And this theoretical framework make a series of predictions about the observational properties of the CV population. And in particular, it predicts that majority of the system should be period bouncer, that we should find majority of the system below the period gap. It also estimates that the CV white dwarf should have an average mass of 0.6 solar masses or smaller, and estimates this, this number for the CV space density. However, when we go and compare this with what we actually observe, we find that actually we find much fewer period bouncer, and we find a higher fraction of CVs above the period gap than predicted by the theory. We also find that, on average, CV white dwarfs are more massive than estimated, and also the observed space density is significantly lower than the theoretical value. However, we can't rule out the presence of observational biases, because period bouncer are characterized by very low mass accretion rates, so they are expected to be intrinsically faint. So if we have an observational bias that prevents us from finding period bouncer, then if we don't find the majority of the population, then of course we will have a higher fraction of system above the period gap, and we will have also a smaller space density. However, this is more complex in the case of the average mass of CV white dwarf, because in her paper from 2011, Monika Zorotovic have shown that actually the problem of the mass in CVs cannot be explained by an observational bias. So maybe this is actually pointing towards incompleteness in the current model of CV evolution. And in order to investigate this agreement, it would be ideal to have a volume-limited sample of system as complete as possible in order to be able to carry out a stringent test between the theoretical prediction and the observation. But as you know, it was very difficult in the past obtaining distances, and in the case of CVs, there were only a handful of them with accurate distance measurements. So it was impossible before Gaia to build a volume-limited sample of CVs. But now we have Gaia, we have accurate parallaxes for about 1.3 billion sources, so we can try to build the first volume-limited sample of CVs. However, the challenge is not only in the distances. At present, we are lacking a list, a catalog of CVs that is up to date. And there are new systems that are constantly discovered weekly. So we really need to, when we started working on this project, we really had to build this catalog in order to have a starting point. And it was a big effort by Elme. She went through the literature, she went through all the available catalogs, and she kept track over the years of all the new CVs that were weekly discovered. And thanks to her wonderful work, we were able to put together, well, she was able to put together a list of 8,000 between CV and CV candidates, which is the starting point for building the first volume-limited sample of CVs. We also need to decide which kind of volume we want to explore, because we want a volume to be large enough in order to contain a fair number of objects, but at the same time we don't want the volume to be too large, because the farther you go, the less accurate are the Gaia distances. And a good compromise between these two extremes is the volume enclosed within 150 parsec. Because accordingly to the theory, you would expect about 140 systems to be located within this volume, and also the Gaia parallaxes for objects like assuming to have a period bouncer at a distance of 150 parsec, which would be the faintest CVs that we can think about, its parallax will be still 5% accurate. So we performed a cross-match between this list and the Gaia DR2 release, and we found, of course, considering the system located within 150 parsec, and we found that 112 CVs are within this volume. And this is their location in the HR diagram. Okay, so here in gray, you have all the Gaia detection within 150 parsec. Here you have the main sequence, and here you have the white dwarf track. I'm not sure if you can see it. And these in pink are all is the result of the cross-match between our CV list and the system within 150 parsec. However, we also have to take into account that not all the Gaia distances are good. Some of them are less accurate than others, and a way to establish which one is good is to look at the astrometric excess noise. So the astrometric excess noise represents the uncertainty, the error on the astrometric solution, and ideally should be 0. So the first cut that you could think to perform is just to consider all the system with an astrometric excess noise of 0. However, we notice that ZCHA, which is in our 150 parsec sample, has an astrometric excess noise of 1. And this Gaia distance of 160 parsec is consistent with the distance derived from independent UV observation. So in order to be more conservative, we decided to assume an astrometric excess noise of 2. And these, in orange, are the systems that have an astrometric excess noise greater than 2, and so we removed them from our sample. And once you remove them, you can see that the population seems to be split in 2. So you have this system that falls where you would expect to find CVs in the HR diagram, and then you have this system that are suspiciously too red. And so, since it's possible that also many CVs that are classified as CVs are actually not really CVs, we went through the literature for each one of the systems. So we searched the literature, we looked at their colors, we looked at their spectra, we looked at their light curves, we looked also for unpublished data in order to establish if they were really CVs. And what we find is that actually these systems are flaring red dwarf, and that there were single white dwarfs, detached binaries, and even a quasar that were mistakenly identified as CVs. And these, of course, are all contaminants. We don't want them, so we just remove them from our sample. However, you can still see that we have these 2 suspicious points, and we also had a third one, which is here, for which the information that we got from the literature were not enough to establish whether they were CVs or not. So for this system, we acquired some ID spectra, and this is how they look like. And since I believe not all of us are experts on CV spectroscopy, I have here 2 CV sample spectra that show you the case of an intermediate mass accretion rate CVs, where the emission is dominated by the accretion disk with these strong emission lines, while here you have a low mass accretion rate CVs. Here you can see the white dwarf from this broad Balmer absorption feature. Here you have the contribution from the secondary, and you still have some emission line. And if you compare this with what we found for the 3 suspicious systems, it's clear that the one of the top is really different from what we would expect. And this turned out being a young stellar object. But if we look at the 2 on the bottom, it's more difficult because they do resemble in appearance what you would expect from cataclysmic variables. However, if you look at their spectra in more details, then you can find that there are some forbidden lines that are typical of young stellar objects but not for CVs. And in the case of the second object, we even have a lithium detection. So all these objects are actually young stellar objects, and of course we remove them from our sample. And these are the survivors from our selection. But this is not all, because with Gaia we also have the opportunity to look for new CVs. Because you can basically look at the average, at the uncertainties associated to the G magnitude, average over the number of observations. And in this region of the HR diagram, where you would expect to find white dwarf, you also expect the uncertainty of the G magnitude to be small, because single white dwarfs are not characterized by intrinsic variability. And so if you look on this region of the HR diagram, looking for systems with anomalous high uncertainties on their G magnitude, then you can find systems that are potential CV candidates. In particular, within 150 parsec, we found these two. And of course, we acquired some ID spectra, and they indeed turn out of being CVs. So thanks to Gaia, we also were able to identify two new CVs within 150 parsec. So I hope you got how painful it was to construct this sample. And by the end, it's composed by only 42 CVs. And we estimated being about 75% complete. And the missing systems are most likely those that show known or low variability. So either polars that don't have accretion disk, so they don't undergo dwarf nova outburst, or nova-likes that have very hot accretion disk, so also dwarf nova outbursts are suppressed, or low mass accretion rate system in which the recurrence time is of the order of decades, so they are not easily detectable. Oops. And now that we have volume-limited sample of CVs, we can look at the composition of the local CV population. And I don't want you to focus on the single subtypes. What's important here is this big slice here. What we find is that a large fraction of CV white dwarf, of CVs host a magnetic white dwarf. About 33% of the system have a magnetic white dwarf. And this is important because all the binary population synthesis studies don't take that into account. And this result is telling us that we can't neglect the presence of these systems anymore. And likely this is not going to be the case, as Diogo will tell us after coffee. And this result is also important because we find magnetic white dwarf in CVs, but if we look at the population of the detached progenitors, there is non-magnetic white dwarf identified in post-common envelope binaries. And so the origin of this magnetic field is still not understood. We can look also at the fraction of period bouncer, and if you consider the two confirmed, then you have a fraction of 5%. If you also include two candidates that, however, are located at the period minimum, so it's difficult to establish if the system has already evolved, becoming a period bouncer, then the fraction can be as high as 10%. But this is quite still far from the theoretical predictions. But the big advantage of having a volume-limited sample of CV is that we can constrain the space density. And we found that the space density is 4.8 10⁻⁶ system per cubic parsec. And I took the freedom of reproducing this plot from Juan's paper. Here you can see our result in comparison with previous observational measurement and in comparison with theoretical prediction. And you can see that with Gaia, for the first time, we were able to reduce the uncertainty on the space density by a factor of 10. And still, we confirm that the space density is lower than predicted by many of the available model of CV evolution. And also, if you look at the period distribution, okay, you can't see it. So there is an histogram in gray here below, in which show that 83% of the system within 150 parsec are located below the period gap. And this is in contrast with the prediction of the standard model, which predicts 99%. So we find a higher fraction of system above the period gap than we predict from the theory. And finally, we also had a look at the mass distribution. So there are 14 systems for which there is published white dwarf mass measurement. And this is their mass distribution, and they have an average mass of 0.83 solar masses. And this is perfectly in agreement with the results from Monica in 2011, and we confirm that this value is higher than predicted by binary population synthesis studies. So if we go back to our table where we had the comparison between theory and now we have our result from the 150 parsec sample, we can see that this disagreement still lasts. So we can rule out the presence of observational biases leading to this disagreement. Instead, we should think about incompleteness in the current model of CV evolution. And a clue for that is also given by the effective temperatures. Why the effective temperature? Well, because angular momentum loss set the mass accretion rate onto the white dwarf. And the mass accretion rate onto the white dwarf basically sets the white dwarf effective temperature because the white dwarf is heated by the compressional heating of the accreted material. So if you measure the effective temperature, you have basically a proxy for measuring the angular momentum loss in the system. So we can use the effective temperature as a function of the orbital period for a comparison with the evolutionary tracks. And here you have in gray all the system for which there is an effective temperature in the literature, just for a comparison. And in color you have in red the non-magnetic CVs within 150 parsec, and in blue the magnetic CVs within 150 parsec. And if we plot the standard model of CV evolution, we can't compare above the period gap because within 150 parsec we only have two systems, so it's not really meaningful. But below the period gap, we have that the evolutionary tracks sits below the observed temperature. And if we include an additional source of angular momentum loss in the model, then we can see that the track goes up and gets into a better agreement with the observed temperature. So there are different models that have been suggested as additional source of angular momentum losses, but I would like to focus in particular on a recent model that seems to resolve many of the observational disagreement. So this model implies the presence of an empirical consequential angular momentum loss mechanism in the model. And it has been developed by Schreiber et al. In 2016, and in a slightly different recipe also by Nellemans et al. So the idea is basically that the presence of an additional angular momentum loss mechanism enlarge the space, the parameter space where the system experiences dynamically unstable mass transfer. So here you have the mass ratio as a function of the secondary mass. And you have this region that is forbidden because it would imply a white dwarf mass more massive than the Chandrasekhar limit. And these are where the systems are dynamically unstable. And so the idea of this model is that there is a consequential angular momentum loss, consequential because it arises from the mass transfer itself, which enlarge this region of the parameter space, making CVs hosting low mass white dwarf unstable for the mass transfer process. So system hosting low mass white dwarf, they will experience dynamically unstable mass transfer process, they would merge, and then they will disappear from the CV population. And this is the part where the model is empirical, because this is tuned in order to reproduce the observed mass distribution of the CV population. So the idea is that this consequential angular momentum loss is more efficient for system hosting low mass white dwarf. And so instead of having a distribution picked at 0.6 solar masses, if you get rid of the system at hosting low mass white dwarf, then you can naturally shift the peak toward higher masses. And this is where the model is empirical, in the sense that it's tuned to solve this problem. However, what's the power of this model is that it also solves for free all the other problems. For example, if you have this CV hosting a low mass white dwarf merging and disappearing from the population, you have fewer systems. And as Diogo will show later, if you include this ECAML in the CV evolution, then the predicted space density is in a very good agreement with our observation. And also, you get rid of the systems that are found preferentially below the period gap, and then you can bring the fraction of CVs below and above the period gap into a better agreement with what we found from Gaia. However, this doesn't work perfectly, because if we look at the fraction of period bouncer CVs, the ECAM model still predicts that a major component of the CV population should be composed by period bouncer. So it predicts a fraction of 80%, while in our sample we find between 5 to 10 systems. So one possible solution for this problem is actually that we are not understanding the evolutionary timescale of the system. So it's possible that the evolution towards the period minimum takes much longer than we estimate, including the ECAM. And so we should look into more details on how these systems evolve. So this is my summary. So we used Gaia, the accurate parallaxes provided by Gaia, to obtain the first volume limited sample of CVs. And thanks to that, we were able to constrain accurately the CV space density, which results significantly lower than predicted by the theory. We also find a higher fraction of CVs above the period gap than is predicted by the standard models, and massive CV white dwarf. And if we consider the ECAM model, we would be able to solve all these three problems. However, the problem of period bouncer will still be there, so we are still not properly understanding the evolution of this system. And I just want to mention again the fact that a large fraction of the CV in the local sample contains magnetic white dwarf, and we can't neglect these results anymore. And I stop here and take questions if there are any. Thank you very much.
in a volume of 40 parsecs and in a much larger volume with other biases. And they claim that the two populations may be different, and that may be in the very local universe, the binary population may be different. And also I'm wondering whether you may lose a small percentage of very peculiar systems that may be significant to understand, I don't know, binary evolution towards type 1a supernovae or accretion-induced collapse, because they are rare, they're very massive and not common.
So I don't think I can comment on the first point, because I would need to know more about the biases and on how the study was carried out. So maybe we can talk.
No, they claim that they can correct for the biases in a much larger volume, and they claim that the binary population in the 40 parsecs volume is skewed, is different from the rest of the galaxy. I don't know if it's true, but it could.
No, but I would say that this still depends on the kind of binary, right? Because each, like CVs have many different discovery methods. So I don't know if this also applies to the binary considered.
Sure, but is it not a concern that it may be
when we
patchy in the galactic distribution, the way binaries form?
Sorry?
So maybe in the galactic distribution overall, the way binaries form or are born may be different in different patches or regions.
So this is just on how binaries form. So
yeah, there may be some local factors that change. Maybe your results are not representative of the galaxy. Is that
it's true that this is a local sample, and we need to do a much more detailed study if we want to go to further distances. But maybe we can talk about that.
Sure, thank you.
And which one was the?
I'm concerned that you may miss all the massive white dwarfs and the interesting and peculiar systems that are interesting, though, for evolution, because the volume is so small.
Well, we do have peculiar system within the 150 parsecs. So we have like an intermediate polar with
massive white dwarfs.
well, I mean,
That's harder,
if you look
I
at the
think.
distribution, we do have massive white dwarf.
Maybe not enough, not really as many as you would find in percentage. Maybe it's too small a sample.
Well,
to
the
tell, yeah.
identification bias for CVs would be actually allow you to find easily system with high masses because they will support higher mass accretion rates, so they will be brighter and they will be easier to find.
Yeah, but maybe the sample is not large enough to tell exactly how many massive white dwarfs we have in the galaxy, because they're rare. That's what I'm saying. I don't know.
I would think about
Okay.
it.
Thank you.
I understand that Gaia is going to fainter magnitudes, but are you sure that the lack of period bouncers is not still a problem of having very faint objects? And the missing problem is just that we are not observing them. It's not that they are not there. We are not observing them.
Yes, so we are discussing about that, but I think this is not the problem, because if we look at the sample, we have very low mass accreting systems, so we have LARPs that are within 150 parsec, that they accrete at about 10 to minus 12 solar masses per year, so it's very low accretion rate, and we are still able to find them. So I don't understand why we are able to find such low mass accreting CVs, but not period bouncer. And my second point is also that I don't think we are fully understanding the evolution of period bouncer, because if we look at the one that are the most favorable candidates, they have much higher temperature than predicted by the theory. So what I think is that actually period bouncer evolve faster here than predicted by the theory, and they are hotter. So I think there is no reason why we shouldn't find them.
You excluded three sources.
Yes.
That they are young stellar objects rather than CVs.
Yes.
Okay. Don't you think that it's quite strange position on the diagram under the main sequence for young stellar objects?
Yes, but these are not CVs, so I didn't think about why they could be there. So I leave this problem for people working on young stellar objects. But I mean, if you look at the spectrum, the feature, what is it? They have lines that you don't expect to see them in CVs. And also, if you try to put a white dwarf in this one, for example, the white dwarf affected temperature would be 8,000 K. And that would be definitely too cold if this was real accretion. So this can't be a CV. Yes. No, it has, yes, yeah, that's a Gaia problem.
But then, okay, so you realize that that's a problem. This quasar has a massive parallax with a small astrometric noise. How does that, does that induce any other bias that we're missing here? I mean, why is this quasar in there in the first place?
No, because I think it acts in a favorable direction, right? So we have systems that are located farther away that we find within 150 parsec. But then when we go and look to each one of them, so I didn't have the time to show it here, but we also did a lot of many checks to verify if the source could be physically located within 150 parsec. So you actually have, it's not like you are missing something, you get more system, and then you can do a series of checks to rule out if they are actually within 150 parsec.
Yeah, I'm not convinced yet. It's a weird bias, this one, so I'm not sure which way.
Yeah, sure.
So thank you very much. Ooh. Thank you very much for having me here. I'm going to switch gears completely. I have to warn you, I arrived 2 hours ago, so if that doesn't go well, then that's okay. So I would like to actually move to citizen science, and I wanted to let you know what the AAVSO can do for you and what we have been doing actually for years and years when it comes to compact binary science. And when it comes to actually discussing projects during the next couple of days, during the whole week actually, keep in mind citizen astronomers. Keep in mind that there's a resource there for you, for your research, that is very ready to actually participate in your projects. And actually I would like to set the stage by presenting a very interesting study that came out of pretty much not my computer. So this one, yes, from Gada and al. And they're talking about the citizen science pyramid, which is a very interesting concept. So what they're saying is at the very bottom of the pyramid, oh, I think I'm going to start here. Here we are. At the very bottom of the pyramid, we have the general public. These are people who are reading press releases. These are people who are interested in astronomy. They find it cool. If they see a telescope, they kind of go and take a look. They are actually participating. Just imagine them like the Oort cloud of astronomy. They're just around. They will read a press release, but they're not really doing anything. And then something happens, and some of them actually become what we call novices in astronomy. Now, novices in astronomy are people who, for some magic reason, buy their first telescope, start reading sky and telescope, become a little bit more interested. Now, according to this particular study, novices in astronomy is just a phase in their life. So most of those go back to the Oort cloud until something happens. And actually, this is where they really become what they call amateur astronomers. Oh, my computer doesn't work today. Here we are. So there's a huge range of them, but these are the individuals who are really actively engaged in astronomy. These are people who join amateur astronomy clubs. They're very active in outreach. There are people who actually do buy telescopes, DSLR cameras, take astrophotos. These are people who participate in citizen science projects such as Galaxy Zoo and Planet Hunters. These are people who are interested in taking data, and these are people who are interested in scientific discovery. These are people who are observing comets and discover supernovae. And these are people who are actually observing variable stars. And from there, at the very top, they're highly skilled. Each and every one of us in this room are belonging here. For us, credentials is really important. But it doesn't really matter if you have a PhD. There are lots of individuals who don't have a degree in astronomy, but they do become specialized in a specific field. So in principle, what this study tells us is that specialization goes from bottom to top. So these people know a little bit about many things, and we know a lot of things about just a little bit. And when we talk about the AAVSO, we talk about this particular group of individuals. And this is what I'm going to call citizen astronomers from now on. Actually, the AAVSO is the only organization that was founded exactly to do citizen astronomy. From the very beginning of our foundation in 1911, we connected professional and amateur astronomers to actually do research. And right now, we are an international organization. We have members, observers, individuals all over the world, both professional and non-professional astronomers who are interested in understanding some of the most dynamic phenomena in the universe, things that we're going to be discussing this week. Most likely you know the AAVSO through VSX. How many of you have heard about VSX? Show of hands. Very nice. So VSX is a super catalog of variable stars. It's been updated non-stop. Last time I talked to you guys, we had about 300,000 objects. Right now we have 700,000 objects, and we're going to cross 1 million in a month. This pretty much is being updated non-stop as new lists of confirmed variable stars are coming out and new information on variable stars. So it's going to be on VSX. But most likely you know us about our database. It does contain more than, actually, go back here, 39 million data points at this point. And you know, if you start thinking about how those data points were collected, these don't come from any pipeline. This is not the result of a huge survey. These are individuals who have been collecting data on about 30,000 light curves, objects that we are interested in and objects we're not interested in, but they're interested in somebody else. So from here, I want to shift a little bit and actually tell you what kind of projects, or give you a sample of projects that individuals have been involved with as part of the AAVSO, and what kind of data exists in that database. And I'd like to start with this. This is one of my favorite stars, GK-Per. This is a nova that transmogrified and became a dwarf nova. The eruption of 1901 was captured. It's really beautiful. And what you see here is visual data, people who actually made measurements of the brightness of the object using their eyes. More than 100 years of data, and at some point you see V magnitude data. It's very interesting to actually take a look at those plots, because you see when non-professional astronomers started getting access to CCD cameras. Also, since Christian Knike is not here, I get to show this. This is SSIG, one of his favorite objects and one of my favorite objects. This is a real light curve. This is more than 100 years of observations. We have about 700 objects like that in our database, ready to be mined, new information coming out, even just by looking historical data. And from one point on, we do have colors. Not only that, we participate very actively in campaigns and alerts, especially when it comes to novae or when it comes to data that are needed in support of a space-based observatory or a spectroscopic data run. These are two examples of campaigns and alerts that we were, so pretty much what happens is that we tell our observers that there's an object that needs observations, or actually sometimes they tell us, especially when novae like this go up to third magnitude. And they're very easy to discover. So these are two of the studies that we contributed to. This is actually the nova where the lithium production was discovered for the first time. And this one is a campaign of V404 SIG, and actually I could spend all day showing you light curves like that. The point here is that we have visual, B, V, R, and I data. And the reason why I really like showing visual data is because most people kind of dismiss them. Do not ignore visual data. It's the black points that you see here. Especially for bright objects, they trace really nicely the brightness variation of a system. That can be a very good way to study what's happening in the very early stages of a nova eruption, for example, when the object is too bright to observe it with your own favorite telescope. We also get them engaged in really crazy projects. So I'm pretty sure that some of you know about this crazy nova in M13.1 that is going off every year. We got engaged in this particular project by Martin Henize and Matt Darnley in 2016. And the main idea was to actually catch this eruption, or the 2016 eruption at that particular time. So pretty much what we did is that we had some of our most experienced observers looking at a blank part of the sky for a year. This nova reaches 18th magnitude and then it declines by 2 magnitudes in 2 nights. So you have to be there when the nova goes off if you want to get any information. So yes, we did have 20 people actually looking at nothing and giving us upper limits for a year in a row. And we managed to actually capture the behavior of this thing. And actually Matt and Martin wrote a very nice paper, included every single one of them here. And it turned out to be late, a very peculiar behavior. So there's a grayscale here that you can't see. The predicted eruption was somewhere here, and this is when it happened. So we started a new campaign in 2017, trying to get the eruption of 2017. There was a prediction, and guess what happened? It was really late. And if you're asking how much late, here we are. December 31, New Year's Eve, 8 o'clock at night, we got an email from an observer in the UK. The eruption is, the nova is off. This kind of dedication, something that you're not going to find very easily. And you get it from these individuals because they love what they're doing, right? And of course, we're going to dedicate a whole morning on Friday about ARSCO, but I want to remind you that ARSCO was known to be a Delta Scuti star, and it was categorized like that, as such, until some observers, for some magic reason, decided to actually observe it, and they found that there is actually a very interesting object, and they participated in this particular paper. So we're talking about individuals whose work appears in literature like very, very frequently, and I'm hoping to see some light curves actually from your own work in this conference. Hint, hint, you can still edit your talk. And of course, we're tracing publications through ADS on how many manuscripts the AAVSO observations are appear every year. So at this point, we really need to think about who these people are and what they can do for us, right? When we're talking about amateur astronomers, what exactly do we mean? So these are individuals who have access to excellent commercial equipment. We're talking about CCD cameras, right now CMOS cameras, filters, automated robotic telescopes. I have observers who observe from Belgium, and they have telescopes at Serra Armazones in Chile, or they observe from the US and have telescopes in Australia. So we're talking about capabilities to remote observe. We are talking about people who are trying to actually push the limit of their budget, or can I say that? Well, 3D print spectrographs, how about that? People who are trying to do the most with the means that they have. And actually, when it comes to commercial equipment, they're getting cheaper and cheaper by the year. So they will have access to bigger and bigger apertures and even better equipment. They do have a diverse skill set. You know, sometimes not having a degree in astronomy is a good thing, simply because they're bringing the expertise from their own field in science, in astronomy. So we're learning from them as we go. Most of them are very technically skilled. They have a degree, they're engineers, they have a science high degree, not in astronomy, biology or chemistry or IT. They're computer scientists, think data reduction. There's a huge pool of them, but not only that, they're everywhere. What that means is that when you really, really, really need data, and somebody's observatory is clouded out or has technical problems, somebody else's is up and running, and they're going to send you data. As simple as that. And of course, they're motivated. You don't have to convince them that your science is cool. They know that your science is cool even before you ask for observations. As simple as that. So what do we do about those people? Or for those people, actually? We train them. We make sure that they know how to take the best data they can take. Again, they don't have a background in astronomy. Most of us suffered in order to learn how to do data acquisition and reduction. So it's not straightforward, right? So we're trying to train them in any means that we can, through manuals, online courses. We have mentoring programs. We have a help desk where we're actually giving them live feedback on the data they submit. We're the ones who are providing them targets of interest. There are billion stars out there. What is of interest for them to observe, and why should they observe it, right? We are providing software for data analysis and reduction. You know, some of them just want to do science themselves and they want to publish a good result. So we're trying to actually help them even understand data analysis techniques in astrophysics, errors, where their error buses are coming, biases, etc. We are doing data quality control. So the main idea is when a light curve comes in our hands, we put it in our repository, in our database, we want you to download it as it is and use it for your research without questioning its quality. So this is actually a big thing that we're spending a lot of time doing. And of course, we're providing international collaboration. So I want you to think of the AAVSO observers as part of your collaboration. A side note, we also have a journal. How many of you know about this journal? Excellent. How many of you have published in this journal? How many of you will publish tomorrow in this journal? So now that IBVS is not curated anymore, perhaps this can be a way for you to publish correct science. Let me be clear. If you have material for a Nature paper, send it to Nature. If you have material for an UpJ paper, send it to UpJ. If you have a small result that does not have a home, send it here, because that small result may help somebody else at some point to do their own research. So for you, think about us when it comes to a project that might need data, time-resolved data. We can actually take them for you. Observers right now can observe all the way down to 19th magnitude, and they're very, very willing and very eager to participate in your campaign. Data quality control, that's what we're doing for you. So even if you have a doubt, even if you download a Lightroom, you're not sure, contact us. We can actually check the data again and again and again for you. In principle, you can do a full project just by using our resources. You can download data from our database. You can even use our online tools, and there is a journal to publish. So if you have a student, for example, who needs a small project for the summer, this could be a really good way of going. Broader impacts. There are lots of funding agencies that are asking for a broader impact component of your project. What is your impact? What are you doing for the public? What are you doing for the taxpayers? And yes, you can actually write that you're going to educate 2 or 3 students, but if you work at the university, newsflash for you, you're a professor, you're supposed to educate 20 students, not 2 or 3. So the AAVSO participating in your project can be your broader impact. And of course, we have a journal that can actually help you with your publication. I'm going to take a little step back and self-advertise something that's coming up. And actually, it is in the making. We have an AAVS spectroscopic database right now. We're launching it in a month. And the main idea is that alongside light curves, to have spectra. And this is something that can actually happen. And these are amateur spectra, by the way, small telescope spectra. So when you have a target that is in need of spectra and photometry, ask for spectra as well. The spectroscopic capabilities right now are increasing, are growing. As I said, there are people who are 3D printing their own spectrographs. And spectrographs are getting fainter and fainter by the day. We can find the spectroscopy database here. And actually, we have 450 spectra right now. We test drove it with a small campaign on SSSIG that went off. And actually, it's being observed right now with TESS. So we do have SSSIG spectra. We have spectra of all kinds of objects in here. And every single spectrum is being validated. So we're providing feedback to observers when we see some kind of problem. And from there on, we hope they correct it. We don't accept spectra that are not validated. We don't accept spectra that are discrepant. As simple as that. So again, while we're talking about multi-messenger astronomy, where we're talking about the newest, the biggest, the coolest, the best, when we're talking about surveys, we also talk about objects that are really interesting to us because we want to study in depth and understand their astrophysics. And I would like you to think about citizen scientists, citizen astronomers, again, as a resource for what you want to do, and come to the AAVSO with your requests. We want to be your collaborator. So for that, I would like to remind you to become a member. For those who are not a member, I'm going to lock the door. This is our webpage, and this is an email. You can actually contact us with any questions, requests, or whatever comes to your mind. And with that, I would like to thank you for your attention, ask if there are any questions for me, and happy coffee break.
It must be.
I'm ready for coffee.
Fantastic, yes. So I wanted to point out that the cloud actually feeds into citizen science and into even professional astronomers, because people who are in the cloud can have a big effect on a big impact on our society. And I'm thinking of my mother, who passed away at age 90 a few months ago, and she was a teacher. Of course, she could make an impact in that way, but she even had a daughter who went into professional astronomy. So there can be very important, and maybe it's more up to us professional astronomers to take care of them and make them interested with our outreach and so on. But they feed into the top of the pyramid, so it's important.
I think that it's up to us to treat them as collaborators. All they need is feedback. All they want is to understand how their data is being used. That's all they want. And from there on, you can have as much data as you want from them.
Hi, Stella. I just wanted to ask, what do you do about coordinating with other groups, like, for example, the CBA group who look at CVs? Do you try to do any coordination? Or?
Yes, we do. And actually, many of the CBA observers are submitting their data in both databases. We do a lot, yes. The answer is yes. All right, let's have coffee. I need coffee.
In the next session to check your talks during the coffee break and make sure that it works on the on the screen here, the projector here. And then we can go and have coffee. So there'll be a coffee break until 11:30, and we'll see you back here after that. Thank you.
Okay, now you can hear me? Yeah, okay. So I would like first to thank the organizers for the invitation so that I could say a few words. Say a few words about my work, about white dwarf binaries. We focus on the formation and the evolution. So thanks. So starting with the formation of this kind of binaries, basically we first have to form the white dwarf as main sequence. And if the separation of the main sequence are sufficiently small, the white dwarf progenitor will fill the Roche lobe at some point. They're in one of the giants phase. So mass transfer will happen, and we can have basically the stable or unstable mass transfer. If we have unstable mass transfer, then we have basically the common envelope phase, and orbit shrinks. If you have stable mass transfer, then likely the binary will expand. So we have two different outcomes from this. And I'm just listing here some of the systems that are in this white dwarf binary range, like CV, symbiotic stars, super soft X-ray sources, this AEM-CVN, detached double white dwarf. All of them are very interesting, but some of them are much more interesting because they are associated with low frequency gravitational waves or supernova 1A. So in this talk, I will focus mainly on CV evolution and the progenitor of these guys here. So one might wonder why we still have to study CV evolution. Like, it seems that we understand. Then there are plenty of reference here and much more. So why should we study this still? It seems quite boring, but the case is that we never really tested the mass transfer rate in the systems in population synthesis. Now it's possible because we have more data. And also we never addressed the white dwarf magnetic field. And if you remember Anna's talk this morning, we cannot neglect this anymore because in the past the fraction was not too high, but now I mean, it's impossible. It's 1/3 of the systems. So the way we are investigating this is with the BSC code. It was developed by Gerald Harley in the beginning of the century. And then we upgraded this code to deal with CV evolution because this code was not designed to do this. So I'm comparing here the Christian Kinniget track, which is the best track we have for CV evolution, with the old version of the code and after the upgrade. So the blue points are the old version and the red one is the new code. So as you can see, we have a very good agreement. So we are quite happy that we managed to implement this in the BSC code. And so far we applied this for computing space densities and also CVs in globular clusters. And then I will show more applications during this talk, but you can also see Christian talk about also using data from this code. So this is a very nice picture for non-magnetic CV evolution. So what happens if we add the white dwarf magnetic field? Just a moment. So if we add the white dwarf magnetic field into the game, what we expect is that we reduce the magnetic braking because the white dwarf magnetosphere will interact with the donor magnetosphere. So somehow this will likely reduce the magnetic braking. And so how this depends on the magnetic moment of the white dwarf. So starting with the red curve here, which has negligible magnetic moment, we have the standard CV evolution that Anna nicely explained. But if we increase the white dwarf magnetic moment, then we drop the mass transfer rate. So this is the mass transfer rate evolution with the orbital period. And as we reduce the magnetic braking, we also reduce the mass transfer rate. And nicely, this also makes the donor less bloated. So this means that we start filling the gap from the lower edge as we increase the magnetic moment. So if we have very strong white dwarf magnetic field, then we basically don't have the gap. So the system remains semi-detached the whole evolution with this black curve here. So we're really happy because this is in excellent agreement with these guys here who proposed this model. So we are very confident that we managed to implement this successfully. So after implementing these, we can start the population synthesis. So we have standard assumptions here for the population synthesis. But two are very important in particular. First is this empirical consequential angular momentum laws that Anna mentioned that can solve several problems in the CV evolution, so we should apply it. Even though we don't know actually the physical reason for that, but it works. Also, the fraction of polars among all CVs is quite high. It's like 28%. So in this kind of investigation, we cannot yet address several types of magnetic CVs, but we can address polars. This is because we don't know actually how to model the spin, for example, evolution. So we cannot really address all types of magnetic CVs, but for polars we can. Then we just assign a probability of 20% for the 28% for the CV to be a polar, or otherwise it would be a non-magnetic CVs. The assumption for the white dwarf magnetic moment is a simple dipole. This is the simplest we can do. Then we can test if this is enough for reproducing the observations. And the white dwarf magnetic field, we don't know actually how they are formed, so we just assumed the observed distribution of polar. So we basically fitted the Gaussian to this distribution and pick randomly when we have a polar. So we compare this with the around 200 CVs from this low one, which is, I think, the largest sample, which is homogeneous. I mean, it's still biased, but it's homogeneous enough and large enough that we are very happy with this sample. And this is thanks to Anna and Boris that compiled this sample. And we can compare. These are CVs with a reliable orbital period. So when we compare with the orbital period, we have here the non-magnetic case, and here is the polar case. So starting with the polars. I think you can see. So this is the observed, this very weak blue histogram, and this strong blue is the simulation. So as you can see in the observation, they don't have the gap. Right? The gap is not pronounced here. And this is nicely explained by this reduced magnetic braking model, because as I mentioned, for sufficiently strong white dwarf magnetic field, they start filling the gap from the lower edge. So it's natural to explain, to expect from this model that we have an increasing function inside the gap. We are very happy because the KS test confirms that indeed we have a nice, we can explain the orbital period distribution. Now with respect to the non-magnetic case, we see these basic features, like the gap, this decreasing of the systems above the gap, this spike around the period minimum, but we clearly predict much more systems below the gap. And this is confirmed by the KS test. It means that we cannot reproduce this orbital period distribution. So we are happy for the polar case, but not this case. And this likely connected with the bias in the lowest sample, because we still have a bias against systems below the gap. To really address this, we should model the CVs using the Sloan colors, and this is in a very complicated way, but I think we would reproduce if we model the bias here. Okay. So as I mentioned, it's quite important to test also the mass transfer rate, because this was not properly done in the past, and I think we have now enough data that we can do this properly. So again, the non-magnetic case is on the left, and on the right the polar. And this is the mass transfer rate against the period. So we can see that mass transfer rates above the gap in the case of polars is from 1 to 2 orders of magnitude smaller, lower than in the non-magnetic case. So this is because of the reduced magnetic break that reduced the mass transfer rate. But this information is not very useful, because we don't measure directly the mass transfer rate in CVs. But as Anna explained, we can use the heating, because of the accretion process, to convert the mass transfer rate into the white dwarf effective temperature. This is a bit difficult to estimate the average mass transfer rates in observations, because we usually don't know the white dwarf mass. But in the simulation we know, so we don't have any problem to compute this, to convert the mass transfer rate into the white dwarf effective temperature. Then when we do this, I think you can see, well, we have here the observation. So this is the white dwarf effective temperature against the orbital period, and the observations are the black points. I hope you can see. So as you can see, for the polars, we are quite good. I mean, we can explain the systems here with this reduced magnetic braking model, because they have very low temperatures. And also for the non-magnetic case, for the CVs below the gap, we are quite good. We can reasonably well explain these temperatures. So we are happy with these two cases, but for the CVs above the gap, no. Because as you can see, the way mass transfer rate evolves is like from longer periods to shorter, then it decreases with the standard magnetic braking prescription. But then I put this arrow here that indicates what is the observational trend of the mass transfer rate. So it seems that the mass transfer rate is actually increasing as the CV approaches the gap, not decreasing. So this is a very a strong failure of the model at some point, at some degree. And also Irma will talk more about another evidence that this model is not very good. So we can think about two obvious possibilities. One is the observational bias, because it's the easiest things to do, to claim, like especially for the ones who run in numerical simulations, like we just claim that there's an observational bias. But in this case, even though we have the bias, it's more likely that there is a problem with the magnetic braking prescription. And this is because, as Anna mentioned, that the fraction of period bouncers we predict is very high. I mean, even if we have still the bias, because I think this fraction should, I think, be larger, we cannot actually, I think, explain this 80% because of observational bias. So most likely, there is a problem with the magnetic break prescription, not only during the CV evolution, but also before, when the pre-CV is becoming a CV. Because you see, if the magnetic braking is doing this, then during the pre-CV phase, the magnetic braking will be very, very small or weak. So the pre-CV phase will last longer. So this means that just a few systems would actually become CVs. So I think this high fraction of period bouncers can also be associated with the magnetic braking. So the conclusion so far is that we have, the reduced magnetic braking model works, and also it seems that this standard prescription for the magnetic brake we usually assume in population synthesis code is not very good. But so far, as I mentioned, I have been assuming that a white dwarf magnetic field comes from the observed distribution. But this is not a very nice thing to do, because the sample might be biased and potentially is biased, and then we don't know how the intrinsic distribution would look like. So what about the origin of the white dwarf magnetic field? So we have basically 4 scenarios that suggest that the white dwarf is built in, the magnetic field is built in the white dwarf. So this fossil is the oldest, and it assumes that this is during the stellar evolution, so the magnetic field will be preserved until the white dwarf formation. We have the mergers between double white dwarfs, that the remnant will have the ideal conditions to have the magnetic field generation. We have the crystallization, which is connected with the age. So as the white dwarf crystallizes, this can also create an environment that allows the magnetic field formation. And we have this dynamo process during the common envelope phase. And this is what I'm going to talk about, because we have simple prescriptions for that. So we can basically test if this makes sense or not. So last year, this Briggs and collaborators, they proposed that with this formulation here, we can explain the observed white dwarf magnetic field in single white dwarf. And then this constant is basically the calibration with respect to the observations. So they claim that the white dwarf magnetic field is proportional to the orbital angular velocity and inversely proportional to the white dwarf angular velocity. So this means that the shorter the orbital period after the common envelope phase, the stronger the magnetic field. Also, the smaller the white dwarf mass, the stronger the white dwarf magnetic field. So using these relations, they use this original version of the BSC code, which I showed that is not good for CV evolution. And they claim that we find that common envelope interaction can explain the observed characteristics of these magnetic systems if the envelope ejection efficiency is low. That's what they claim in the abstract. And what I'm going to show you that this is not true, unfortunately, because this is a very nice theory, but it doesn't work. So this is, and I'll explain why it doesn't work. This is the white dwarf magnetic field predicted for all CVs in the simulation. So what I did was the same as before, but instead of assuming a probability of being a polar or not, I just computed the white dwarf magnetic field. So this is the white dwarf magnetic field of all CV. So you see that we cannot explain the polar distribution. Because this is the sort of magnetic field we see in intermediate polars. But what is most surprising is that this theory predicts that basically more than 90% of all CVs should be magnetic. Because if this depends on the period, we have a maximum period that we can form a CV during a Hubble time. This means that CVs are, after the common envelope phase, we'll have like 1-2 days. Then this is already enough to make this white dwarf magnetic field greater than 1 megagauss. And this is what I'm saying, that this is a magnetic CV. And if you remember Anna's talk, this is a very high fraction, but it's not even close to 94%. Also, the fraction of polars among all these magnetic CVs is pretty low. And also this comes from Anna's work. The fraction of polars among magnetic CVs is like 80%. But the prediction of the model is very small. With respect to post-common envelope binaries, this is something that they didn't even mention. So I'm showing here the white dwarf magnetic field against the orbital period. And again, the black points are the observations, but in this case, the prepolars, the 10 we know. And you can see that this model can explain these two systems here. But it fails in explaining most of the prepolars because they have much stronger white dwarf magnetic fields than this theory can predict for this certain period. So it fails in explaining the observed properties of prepolars in this diagram. There's also very weird prediction again about the fraction of magnetic post-common envelope binaries, because it predicts that it should be at least 80%. But the only ones we know are the prepolars, so this is very, very bad. So what I can conclude from that is that either this formulation, this mathematical formulation, should be revised, because in the way it is proposed by Briggs and collaborated doesn't work, or there's another process that explains the white dwarf magnetic field in CVs, or in polars, more specifically. So I end the CV evolution part of this talk, and in the remaining I will concentrate a bit on the white dwarf main sequence formation. This is an ongoing project. And we expect very nice things coming from this, because we have a much broader range of binaries. So if you remember, in the beginning I mentioned that we have stable and unstable mass transfer to form the white dwarf main sequence binary. But if you have stable mass transfer, the system likely expands, and if we have common envelope phase, the unstable mass transfer, the system shrinks. But one thing that is not really considered in population synthesis is when we have a case where the mass transfer is non-conservative, which means that we have mass loss from the system. So why we should investigate non-conservative but stable mass transfer? Stable but non-conservative mass transfer. First, because this is more realistic. It's the case in which all the mass coming from the giant goes to the main sequence is very ideal. These affect the stability criteria in the sense that more systems will undergo a stable mass transfer instead of common envelope phase. This might also explain the orbital periods that are found in white dwarf with more massive main sequence and symbiotic stars. But then Stefania, and Joanna will talk more about these two types of objects here. But changing this, we can also potentially change the supernova 1A rates. Not only via the single degenerate scenario, but also in the double degenerate scenario, because these systems likely will produce double white dwarfs. And some of them will produce supernova 1A as they are. And so this is a plot showing the stability criteria to define if it's a stable or unstable mass transfer. So we have the mass ratio against the fraction of mass in the core of the giant. This line here is the stability criteria for the conservative case. So this means that everything above this line will have common envelope phase. So I'm showing here 4 cases in which we have this accretion efficiency onto the main sequence. So beta equals 1 means that we have the conservative case. It means that all mass goes to the main sequence. Then we have different efficiencies here. And as you can see, as we decrease the efficiency, we increase the mass loss from the system, we allow more systems to undergo stable mass transfer. So I'm plotting here only, the points are those with stable mass transfer. So you can see we can increase the number of systems. And why it's important to have like more with stable or less, or more with common envelope is just because the outcome is quite different. For example, here is an example showing 2 main sequences with mass 1.2 and 1.1. And the colors indicate the initial period of this binary. So what I'm showing here is the orbital period evolution against the mass of the giant. And here's the mass transfer rate against the mass of the giant. So the evolution in this panel is like from the right to the left. So initially, if you have this stable mass transfer, initially you have mass transfer in a thermal time scale. So it's pretty high, and then it becomes smaller, and it goes on a nuclear time scale. This is the longest part, and this is responsible for this very nice increase in the period. So you see that, of course, this is just one example, but we can see that this can populate this region between about 100 and about 1,000 days. And this is really hard to get this when we only consider the common envelope phase, because we expect much shorter orbital periods. So this is very nice, actually, because it can populate this region. But you see that starting, for example, with, 50 days, then we can end up with 500 days. So it's very nice, actually. But, these are MESA simulations, so our goal is to calibrate the BSC code with this kind of detailed evolution. This is because MESA is, okay. This is because, MESA is very good, but it takes too long to run. With the BSC, you can run in, 1 million. With this binary population synthesis code, like this BSC, Star Trek, binary C, you can run like millions of binaries in the time scale that MESA can run 1. So it's important to have the population synthesis code, because then we can really make the population synthesis. So this is the preliminary result. I mean, when I compare in the BSC with MESA, and see that it's somehow good, but it's not very good. But you know, we have this initial feature here, but the problem is that in BSC, the binary is not expanding in a rate good enough. So actually, the system, like, you know, blows up. This is what I have to do, but this is very encouraging anyways, because it seems that this is something doable, and it's very nice. So I start with the summary. So the first point, I think it's important from this talk, is that the reduced magnetic braking model seems to work and explain quite well the properties of polars. Unfortunately, the way Briggs and collaborates formulated this idea about the white dwarf magnetic field generation during common envelope phase, it doesn't work because it cannot explain the properties of polars and prepolars. It seems there is a problem with the magnetic braking prescription because we predicted wrong white dwarf effective temperatures and a much higher fraction of period bouncers than observed. And the last one is that we should consider in binary models the stable plus non-conservative mass transfer and eventually calibrate this how the efficiency of the accretion comparing with observation, because this is very nice and quite important. I think it's not well addressed in this kind of investigations. Well, thank you.
So let's assume the observers are right. Do you have an opinion from your simulations if the number of prepolars versus the number of polars we see makes sense? My feeling is that we have just too few prepolars, but
the problem is that we don't know actually how they are formed. One thing, for example, because we don't know actually, so we cannot say anything. But one thing that is very interesting for prepolar is about the age. I mean, they're very cool. The white dwarf is very cool. In all these cases, I mean, below 10,000 Kelvin. So this seems to be connected with the age, maybe. But you know, we have just a few and we don't know. Maybe this common envelope phase stuff is correct, I know, but it needs upgrades. So.
Could it be a situation that the problems with modeling polars reflects a problem with our understanding mass transfer in systems? So if we have really strong magnetic field of the white dwarf, it could act ejecting material or even increase mass transfer. So getting lower pressure in the atmosphere of the companion. Maybe these problems comes from just we incorrectly treat the mass transfer in case of polars.
Yeah, it might be, but I think this is. I mean, I think it. I mean, of course, we have only 3 points here, but this suggests that the mass transfer is being reduced. And if you know, I mean, if you have a look at this is the region in which we only expect gravitational radiation. So this part here, magnetic braking is operating somehow, but here it's only gravitational radiation. I mean, what I'm saying is that this explains this 3 points, but we only have 3 points. So we need more polars with this white dwarf, and then we can see actually if we should see like higher mass transfer rates or smaller. But this, of course, assuming that you know this here is true, which I'm not sure if this is entirely correct. But, you know.
So this is more of a comment. In polars, the white dwarfs may have multipolar magnetic field, not just dipolar, and the field strength observers have measured may reflect the multipolar component, whereas what matters for evolution is usually just the dipole component. So there may be some difference there. So that's something more a comment to observers to pay attention to that potential issue.
Okay, great.
Okay, so I'd like to thank the organizers for inviting me to give this talk. I'm going to talk about the donor stars in compact white dwarf binaries, and I can only apologize for the bias and lack of completeness in this review. If you want me to give you an unbiased and comprehensive review, you should give me an entire day. So I'm only going to focus really on main sequence donors in CVs. There'll be no discussion, for example, of evolved donors, and no discussion about the formation of AM-Cam-Ben stars, but there are lots of talks later on that kind of thing. So this is the thesis of my talk. I'm going to try and argue that, as we all know, it's the angular momentum loss that really drives the evolution of close binaries, and that if you want to measure the angular momentum loss in close binaries, you want to determine it empirically, then donor star properties are the way to do it. They're a great probe of the angular momentum loss. If you do this, I think the conclusions that you find is that the donor star properties in close binaries support some sort of consequential angular momentum loss model. And I'm going to talk a little bit about the kind of magnetic braking laws that we might expect to see in CVs based on our understanding of the magnetic fields and spin downs of single stars. So I'm going to start off with my first point, which is we can all go back to school a little bit, and I'll explain why angular momentum loss is important for close binary evolution. I'm going to explain the evolution of a CV very badly. All models are wrong, but some models are useful, and it's kind of useful to think of mass transfer as a multi-step process. So we start with mass transfer from the less massive donor to the white dwarf, and that separates the system, and the system detaches, and that stops mass transfer. And if the donor star has enough time to restore thermal equilibrium, it'll shrink in response to mass transfer slightly. It's not the end of the story, of course, because we have some angular momentum loss, which shrinks the orbit. Right? That brings the donor back into contact with its Roche lobe, and therefore it's the angular momentum loss that drives the mass loss and evolves the binary to shorter periods. And in this case, the mass transfer occurs at a rate which is determined by the angular momentum loss timescale. Now we can understand the kind of second part of my case, is which we should use donor star masses and radii as a probe of this angular momentum loss. And the reason is that there are two competing processes here, right? The first is the angular momentum loss from the orbit, which will shrink the orbit, and that occurs on the angular momentum loss timescale. And the second is the response of the donor to the mass loss, and that's going to occur on the thermal timescale. And in white dwarf binaries with main sequence donors, there's a bit of a stroke of luck, really, that those two timescales are comparable. So we're in a regime where the thermal timescale is of the same order of magnitude as the mass transfer timescale. And with apologies to Christian Koeniger, Joe Patterson, and Isabel Baraf, I'm going to kind of crib their 2011 paper and argue what this means for the donor stars. The important point is that the donor star is responding to the mass loss and trying to restore thermal equilibrium, right? But it can't do that because it's losing mass at a rate which is comparable to its thermal timescale. And that means the donor star is driven slightly out of thermal equilibrium and will be bloated compared to main sequence stars. This is the really important point, because the amount of bloating that we get, the extra size that you see in your donor star, depends on the relationship between the thermal timescale and the mass loss timescale, or the angular momentum loss timescale. And this makes CV donors a good probe of the angular momentum loss. Now, the more pernickety, troublesome members of the audience will be wanting to raise their hands at this point and saying, what about fluctuations in the mass loss, right? So we know what kind of timescale a donor star will adjust its radius to. So Stella et al., for example, in 96 showed the donor radii will adapt its radius to whatever the current mass loss rate is on a timescale which is about 1/20th of its thermal timescale. And this is a lovely number because it's much shorter than the time scale on which the binary evolves, which means that the donor will forget its initial conditions, right? And all binaries which experience the same mass loss should occur on a common track. But this timescale is also longer than any of the timescales on which we expect mass transfer rate variations to occur. And that means that if your mass loss rate goes up for a few 100,000 years, the donor star doesn't care about it, right? It'll average it out on timescales of about 10 to the 6, 10 to the 8 years. This means that CV donors are awesome probes of angular momentum loss. In fact, donor star radii in close binaries are the best probes of the angular momentum loss. Here's a worked example. So this is 2 evolutionary tracks from Christian Knigge. The only difference in these 2 tracks is the angular momentum loss rate. Below the orbital period gap here, you've got the blue track, which has enhanced angular momentum loss at about 2.5 times the rate you'd expect for gravitational radiation. And you've got some kind of canonical donor of 0.1 solar masses here, and it fills its Roche lobe at some orbital period. But if you increase the mass loss rate, you drive it out of thermal equilibrium, the donor gets bigger, and it fills its Roche lobe at a longer orbital period. And so move on to this track here. And we've heard a lot about how uncertain angular momentum loss is in binaries, but it turns out it's easy. We just go out and we measure a whole bunch of donor star masses and their orbital periods. We plot them on the track, and we then know what our angular momentum loss rates are, and we can go on and run population synthesis models. Unfortunately, it isn't quite as simple as we'd like, right? All of this is based on the fact that we can measure the degree of bloating compared to the equilibrium radius, the main sequence radius of a donor star of that mass. And this, of course, assumes that we know what that equilibrium radius actually should be, right? But there are three complications. The first one is distortion of the stars, right? So these stars are not in a spherical potential. They're in the Roche lobe geometry, and that has an effect on their equilibrium radius. I would argue it's relatively simple to model this, and it's a relatively small effect. It's of order 5%. There are several references here showing how you want to include it if you'd like to. But it's a relatively straightforward thing to do. We've also put these stars right next to a hot white dwarf and an accretion flow, and it's irradiating the donors. And that's going to change the thermal energy balance and inflate the donor stars. You can model this as well. It's slightly trickier to do and slightly more uncertain, but it turns out that it's a small effect, right? So it's going to change the donor radii by about 1 to 3%. And we can include this in our models if we like. It's a small perturbation. The next thing is what actually is the radius of an equilibrium main sequence star? Right? And that sounds like the easiest question of all, but actually this is probably the biggest problem. And the reason this is maybe the biggest problem is that main sequence stars in thermal equilibrium are too big. Right? They're larger than models predict by something like 7 to 10%. We know this from eclipsing binaries, from single stars, from interferometry. It's a robust result. And this is really tricky. And it's really tricky for this reason. This is a result from Stephen Parsons, where he measured the radii of main sequence stars in a whole lot of post-common envelope binaries and compiled all the existing main sequence mass radius determinations from the literature. And what's plotted here is the measured radius divided by the theoretical radius. And they're pretty much, although not entirely, all larger than 1. All right, so 1 is what we'd expect if the main sequence models were good. And I've plotted this against orbital period. But the thing that really kills us here, the really annoying problem, is there seems to be some intrinsic scatter here. Right, so if we look down at these short period chaps over here, we have stars at the same orbital period, some of which seem to be smaller than the models predict, and some of which seem to be larger than the models predict. The kind of average inflation here is about 7%. And so if you're running an evolutionary model, what someone like Christian Knigge would do is apply a standard 7% inflation to all of his stars. But there are some stars that don't seem to be inflated at all. And worse than that, at the moment, we have no way of predicting which stars are inflated and which are not, because there seems to be no obvious link between the radius discrepancy and parameters of the star, like rotation rate, or age, or metallicity, or mass. So it's currently impossible to predict the expansion for any given donor star. So whilst the other two kind of little niggles are fairly easy to deal with. This is a larger problem, which for now I'm going to sweep under the carpet and assume that we can ignore it and just apply a constant inflation to all of our donor stars in our models. And with that in mind, I'm going to go on a whirlwind and extremely biased history of what we've learned from studying donors in cataclysmic variables. So CV donors are quite hard to see. They're relatively faint compared to the white dwarf and the accretion flow, and so it's not surprising really that the early history is slightly muddled. For example, if we look at these two papers, 1983, Echevarria publishes a paper saying that CV donors look like main sequence stars in terms of their spectral type. So if you look at a 0.1 solar mass CV donor, has the same spectral type as a 0.1 solar mass. Sorry, it's the other way around. It has a later spectral type than a 0.1 solar mass main sequence star. Whereas we have a 1984 paper by Joe Patterson and a 1983 paper from Ruiter arguing that CV donors have exactly the same spectral type as main sequence stars of the same mass. And this kind of confusion persists for about 10 years when it turns out that Brian Warner kind of looks at the same sample as Echevarria with a more careful analysis and says that no, Joe was right all along. CV donors have the same spectral type as you would expect from a main sequence donor based on its mass. So if you take a CV donor of 0.2 solar masses, it has the same temperature as a main sequence star. And then, so observations of CV donors start coming in. We have spectroscopic observations, measurements of a few masses. And by the end of the kind of 1990s, we have a few seminal papers, one by Boyerman showing that CV donors compared to a main sequence star are inflated, right? So compared to our expectations, they should be bloated, and indeed they are. And Smith and Dillon perform a similar analysis where they combine what they determine to be accurate measurements of the CV donor masses, and at this point in 1998 there were 14. Right, and they compared they confirmed Boyerman's results. So we have a kind of we have a coherent picture emerging that CV donors are inflated, as we'd expect, but it's based on a very small sample of only 14 systems. And it takes until 2005 for this situation to be kind of improved, if you like. I mean, all the time people are observing 1 or 2 CV donors, but it's hard, tiresome work. But Joe Patterson takes a completely different approach, which is instead of kind of using eclipsing binaries and measuring precise masses for systems one at a time, he actually uses systems in outbursts, and he uses the precession of the disk. So that you get these super humps as the disk precesses, and the period of that precession is related to the mass ratio. And so you can measure the period of the precession very easily and quickly. You can use an empirical relationship to get the mass ratio. Assume an average white dwarf mass. It's very quick and dirty, but if you do it that way, you get masses for hundreds of donors. Right? So we've gone from 14 systems to 100 systems, and this gives us a much clearer picture of what the donor stars in CVs actually look like. And so in 2006, Christian Kniger takes this sample and compiles an empirical donor sequence. So it just says, what are the properties of CV donors as a function of orbital period, if you like. And then in the intermittent, between 2011 and 2006 and 2011, I start working on this problem by measuring the masses of CV donors in systems where we can't see the donor directly. So you can do this by measuring the shape of the primary eclipse and modeling all of the structures that you can see in primary eclipse, and that can give you accurate and precise masses for large numbers of donor stars. And this is kind of, we start seeing good masses for short period systems, including the first masses for period bounce systems and systems with substellar donor stars. And by now we've got a kind of decent sample of CV donor properties, and the seminal work on CV evolution might be Christian Kniger's 2011 paper, which has 63 pages of goodness, and basically takes this donor sample and says, what can we learn about CV evolution and close binary evolution from CV donors? So this is my attempt to summarize those 63 pages in one slide in 2 minutes. So this is a diagram of masses and orbital period, and these are the systems. The superhumping systems are shown as the black squares, and the eclipsing systems are shown in, no, they're not shown here. They should be in red, but it doesn't come across very well in this slide. So the standard canonical CV evolution model is shown by this dashed line here, and it has some problems. It predicts an orbital period minimum, which is too short. It lies above all of the systems in the mass orbital period donor track. And so Christian's attempt to fix this is a revised model in which he slightly reduces the amount of magnetic braking you have above the period gap and arbitrarily increases the angular momentum loss below the gap by a factor of 2.5. He uses the same form as you would have for gravitational radiation, but just increases it by a factor of 2.5. And it does a pretty good job of explaining the systems. There's still a fair amount of scatter in the masses here, and there aren't really very many systems, particularly around period minimum and at very short orbital periods. So since then, we've been busy at work trying to add more systems to this. And we have, over the last decade, measured maybe masses for 20 more eclipsing binaries. It's an extremely large amount of work, mostly done by my ex-PhD student, Martin McAllister. And we also reanalyzed this relationship between the disk precession period and the mass ratio, recalibrated that with some of our new systems, including systems of very short orbital periods and beyond the period bounce. We have 225 donor masses from the disk precession periods. And this is, thanks to a tremendous effort by Martin, but also thanks to the AAVSO and amateur astronomers who measured many of these superhump periods. So on this diagram, the superhump periods are shown in sort of grey circles. Black and green dots are masses measured by my group, and blue circles shown in a faint colour to minimise their importance is work done by other people. And let's have a look at some of the most important conclusions I think we can learn from what we know about CV donors today. Okay, so the first thing to say is that, actually let's go back and look at the large slide. The first thing to say is I've shown here the same two tracks from Christian Koenige's paper. And so this track here is the standard CV model with only only gravitational radiation below the gap. And if you look at the masses of the donor stars from just below the period gap all the way down to the period minimum, that actually does a pretty good job of explaining the donor star masses at a given orbital period. That means that these donor stars don't really need an additional source of angular momentum loss to explain their properties. It's perfectly consistent with just gravitational radiation alone. By the time we get down to the period minimum, these systems are no longer well explained by the standard track. Right? So the standard track comes down here. We know it underpredicts the period minimum, and so unsurprisingly, these systems start to deviate from the standard track. We have very little scatter around this relationship. Right? The scatter around this relationship, the intrinsic scatter, is only 2%, 3%, 0.005 solar radii. Okay. That's interesting because the observations of main sequence stars seem to imply an intrinsic scatter of nearly 10%. We don't see that in CV donors. And if we look at the superhumping systems alone, around 30% of our systems are beyond the period bounce, right, which is roughly consistent with what Anna finds from her volume limited sample, but slightly higher. So if we look at the kind of angular momentum loss law we need in order to explain these observations, right, immediately below the period gap, we don't need any extra angular momentum loss. By the time we get down to the period minimum, we need an angular momentum loss rate which is about 2 times gravitational radiation. Right? But the gravitational radiation is dropping all the time, so what this actually turns out is we need a roughly constant amount of angular momentum loss for systems below the gap, which is pretty much consistent with these eCamel models that we have from, for example, from Matthias Schreiber, who has an angular momentum loss rate which is just proportional to the white dwarf mass, which is constant. All right, so these models from 2016 give an angular momentum loss law which is roughly what we would need to explain the donor properties. However, you've got a kind of caveat that it may also be consistent with some residual magnetic braking, right? If magnetic braking doesn't entirely go away. And it depends what your wind braking laws are, right? Which brings us to the fact that disrupted magnetic braking may work after all. And I say after all, and everyone in the previous talks has just been assuming that it works. But why would we think that it doesn't work? Well, the whole thing is predicated on the idea that the magnetic field, and therefore magnetic braking, goes away when the donor star becomes fully convective. This is a Zeeman Doppler imaging map of a magnetic field on an M6 star. Right, it has a strong 2 kilogauss dipolar field. Right, that's the same magnetic field as we see on young solar analogs, but yet we're expected to believe that this star is not going to spin down like the young sun did. Why? Here's some X-ray measurements, right? X-rays are a tremendously good measure of the magnetic flux which is threading the surface of the star. So here's a compilation of X-ray measurements of stars from Wright and Drake versus rotation period on the bottom. In very light grey points, I've shown partially convective stars. And you have this classic relationship where X-rays saturate at low rotation periods and then drop off. And the dark points are fully convective stars. And they have exactly the same relationship. They have exactly the same magnetic flux threading the surface. And the real killer argument is that thanks to Kepler and large photometric surveys, we now have much better collections of rotation rates for single stars. So the purple points here are rotation rates of single stars from Kepler, from Amy McQuillan. And the green points are Elizabeth Newton's compilations of rotation rates for fully convective M-dwarfs from the M-Earth survey. Right, and we have plenty of rapidly rotating M-dwarfs down here. But if M-dwarfs don't spin down, fully convective M-dwarfs don't spin down, where did all these M-dwarfs at 100 days come from? All of this really seems to argue there's no change in the magnetic field strength, and perhaps there's no change in the spin down at the convective boundary. But, right, our get out of jail card is that we do not need the strength of the magnetic field to change for the magnetic braking to change. Right? As coaches pointed out, only the dipolar component of the field reaches far enough away from the star to actually influence magnetic braking. And this is a very old suggestion. So this is a paper from 1989 by Tarm and Sproit, which suggests that increasing the complexity of the magnetic field can explain the period minimum. So they suggest that magnetic complexity increases at the convective boundary, and if you rearrange the field from a low order to a high order multipole, you can change the fraction of open field lines by a factor of up to 200, right? And that produces a commensurate loss in stellar wind and therefore magnetic braking. And because the total field strength doesn't change, right, you can do that without a sudden decline in magnetic activity. So these stars have the same magnetic field strengths, they're just as active, but they have a more complex magnetic field. Now we can measure the magnetic field complexity. Right? So for example, Zeeman Doppler imaging measures the large scale field. It will tell you how strong the dipolar component is. But if you look at, say, Zeeman broadening of the spectral lines, that measures the total field strength. Right? So you can compare the large scale field strength to the total field strength, and you can see how complex the magnetic field is. And there's growing evidence that B-field, magnetic field complexity, is different for fully convective stars. Right, there are some references here that you can go and read in your own time when you look at copies of my slides. And it is apparent that the complexity of fully convective stars is somehow different to that of partially convective stars. But it's very early days, the observational picture is confused, and there's no unifying theory about what determines magnetic field complexity as yet. Certainly not one that I believe. There's one theory which does exist and has been applied to CV evolution, right, which is one from Jeremy Drake and Cecilia Garaffo's group. And they have a model in which they've coupled their own MHD simulations of magnetic winds, which are shown on the right, versus magnetic fields of increasing complexity. And then this is just showing that as the complexity increases along the x-axis, the angular momentum loss drops as the field becomes more complex. They couple that with basically an ad hoc formula for how complexity might change as the orbital period of the binary changes. Right, so shown in these points are measurements of the complexity of fully convective M-dwarfs, and shown in a dashed line is their model for how complexity changes with rotation period. And the key point here is that the complexity increases very, very steeply as the period gap approaches. And so a very rapid rise in complexity creates a rapid drop in angular momentum loss, which could be what you need to explain the period gap, sorry. So on the right here, I've kind of plotted what their magnetic braking law looks like as a function of orbital period for white dwarf donors versus magnetic braking. And you can see that there's no disruption of magnetic braking here. Really what's happening is that it's just dropping quickly enough so that the donor can restore thermal equilibrium and move and detach from its Roche lobe. If you believe their magnetic windbreaking model, you can't explain our donor properties, right? Because below the gap, their windbreaking angular momentum loss is hundreds of times lower than gravitational radiation. So it can't produce, and worse, it kind of, as you get to very short orbital periods, it gets smaller and smaller, so it can't explain the donor radii with this particular braking law. But for people reading this paper and getting excited that CV evolution is solved and this is the braking law we should use, it's worth pointing out that this relationship between complexity and period really is essentially invented. Right? It's invented and tuned to fit the observations, and it may not reflect real life. I want to give you an example of how this may not reflect real life, and I'm going to do so by going back to this system here. This is actually part of a binary. This is UV SETI, and it's part of a binary. Its companion is also an M6 star. It has the same mass, it has the same age, it has the same effective temperature, it has the same rotation rate, and it has an extremely weak dipole component and a very complex magnetic field. All right. So this is to ram home the point that we don't know what causes magnetic field complexity to vary, but it's certainly not a single and smooth function of rotation period. So I'm quite confident that magnetic complexity is explaining the period gap and is important for disruptive magnetic braking in some way. The bad news is that we don't know from observations of single stars what kind of relationship we should be using for our angular momentum loss laws just yet. Okay, so my now unsurprising conclusions, because you've seen this slide several times, I'm just going to leave that up and answer any questions that people have. Okay, I don't think they're so different, right? I think so. Anna's paper, I think, is 5 to 10%. Is that correct? And 75% completeness in the whole sample. So if you assume that all of the missing systems are period bouncers, that takes you to 30%. The other side of the argument is that we're only looking at these outbursting systems that show these superhumps to get 30%. And those systems are biased towards extreme mass ratios, which is the period bounce systems. So that 30% number from our paper is probably biased high. Anna's number is probably biased somewhere low, and it's somewhere between 10 and 30% is the true number.
Can you go back to your McAllister 2018 slide with the mass measurements? Okay, so I asked the question before we get there.
Okay.
If you remove all but the good points, and the good points are the black ones.
Yeah, keep going.
Do you believe that there's evidence for bloating?
All but, you mean all but the eclipsing points?
Yes.
Yes. Okay, in the sense that you have these points over here which shouldn't be there. And these are very accurately measured donor star masses and radii. But also not looking at the points at all, just looking at the period minimum.
I was thinking above the gap.
Oh, above the gap. Oh, I have no idea what's going on above the gap, right? There's a reason why my talk focused only on these objects, right? Above the gap, there are very, very few systems, and we're trying our hardest to improve that, but it's actually much harder to measure masses in those systems. And B, I think there's a very large intrinsic scatter. Right? I genuinely think, I mean, if you just look at these systems and IPPEG, there is above the gap is more complicated. Let's just put it that way.
I just want to make a small comment, Stuart. You made me feel a very odd 35-year deja vu feeling. When I wrote that paper in 1983, my concern was that I was always sure that the donor stars were bloated for larger periods. I'm glad that this has become a subject of many years of discussion.
Thank you for the comment.
It is regarding this angular momentum loss, and it must be also involved with the underlying accretion process. I'm just wondering why, I believe, as you know, underlying accretion process itself is quite uncertain in terms of viscosity and all the field, large scale field or small scale field. Why, maybe I'm missing something, but why people are not also more involved in trying to understand whether problem is with the underlying accretion process, whether we know for sure what exactly is happening in terms of accretion and which helps in transferring angular momentum, or of course what you are saying, those are also important points, but my question is whether underlying accretion process itself is well understood in this context.
I think, yeah, it's a good question. In terms of looking at the accretion process and trying to understand its consequences on angular momentum loss, one big question is how much mass is lost from the system during the accretion process, because that has an effect on the evolution of the system. You can try and study that from looking at the accretion itself, but my approach is slightly different, which is to try and go and measure these donor star properties and say, okay, well, what should your evolution look like? And then how do we get there? Right? So if I give theorists a target to hit for the long-term evolution of the system looks like this, right? So the angular momentum loss over kind of 10 to the 6, 10 to the 7 year timescales is this number at every orbital period. And if you need 10% mass loss from the accretion rate to drive that, then fine, then that's what we do. Rather than going out and looking at individual systems and what their accretion looks like, because that's very messy, and it's also very short timescale. So you can look at one system and its accretion is very different from 1 week to the next. But the evolution only cares about million-year timescales.
Just a short suggestion for the presentation with a very good idea to show how system getting detached, but the accretion disk in this form should disappear.
Well, this is why all models are wrong, right? Because this is not what actually happens.
And hence I am not prepared because I was busy with other stuff. I'm going to talk about this donor star of V1082 Sagittarius. I'm not characterizing it here because we actually don't know what is it. And I tried to do the infrared spectroscopy to make it clear. And we will see what happens. This is a strange object that we discovered a couple of years ago. I already published 3 or 4 papers on it. And I suspect from the ADS numbers that I'm the only one who is reading these papers. So my introduction is larger than the talk, but I think it is important that you get hold of this system because it might be a clue to some answers or questions to the closed binaries. So it's 20.8 hour binary. The donor star is a chromospherically active K star. It is probably strongly magnetic system. We have many non-direct evidences that it works like a polar, the accretion in this system. And there are these prepolars containing M stars, and there is an explanation for how they work. Basically, the wind of the M star is captured by the magnetic field of the white dwarf, the strong magnetic field of the white dwarf, and they are connected. Their magnetic fields are connected, so the mass accretion occurs M star is not filling, nearly filling or not filling the Rho slope, so the mass accretion occurs by capturing the wind from the M stars and accreting into the magnetic white dwarf. It kind of works in M stars because the luminosity, X-ray luminosity there, and the mass accretion rate estimated from X-ray is low. It's 10 to minus 13 to 10 to minus 14 solar masses per year, which is kind of explainable by if you capture all the wind from the M star. Now, in this object, the secondary star is an early K star, and first of all, it can be much more active magnetically, but then the mass accretion rate is too high. I'll come back to that later. So, first of all, you can observe V1082 Sagittarius like that, where you see a K star and you see some ultraviolet excess, which shows that there is a white dwarf it's a binary system with a white dwarf. And we will have many talks from Stephen, Odette, and Stefania about searching for such kind of pre-cataclysmic variables or post-common envelope binaries. So this was a serendipitous discovery of such a system, not in their lists. But the trick is that this system usually looks like a cataclysmic variable. It doesn't look like I showed you. The minimums occur very regularly, cyclically, every 29, 30 days, during which you see only K star. But the rest of the time, it looks like a CV with huge emission lines, a lot of helium-2, and a very variable ultraviolet excess. So if you look at these minimums, which was done by K2, you see this marked minimum. You can see that the light curve has a period of the binary, and it probably evidence that the secondary star doesn't fill its Rho slope, because otherwise there should be a double hump light curve, or the system inclination is extremely low, which also doesn't work because we see the secondary, we see the emission lines during the active phase, which are similar to polars, although the phasing of the lines is not exactly like polars. And as you see here, the spots where the different components of emission lines comes from one is near the white dwarf, but the other one is a very off usual place where it should be. So we believe that this system, as I explained, is a detached binary, and the mass accretion occurs by the magnetic lines. So here is the spectra, relatively high resolution spectra, and the radial velocity curve of the secondary. We figured from these observations that the secondary is something around K2. And we measured the rotational velocity of the secondary. So we deduced the parameters of the system. The mass of the white dwarf comes from the X-ray observations. The donor star comes from just from the spectral type. So if you put these numbers, and this is the rotational velocity limits, this is the luminosity of the secondary star, this is the Rho slope. So clearly, if you put a nearly main sequence K2 star into this diagram, it doesn't fill its Rho slope, and the system should be detached. However, in detached systems, again, going back to the X-rays and measurements of the accretion and mass of the white dwarf, accretion rate reaches like several 2 to 10⁻⁹ solar masses per year, and it's a problem. The reason that this system is not attracting a lot of attention, because I believe 80% of present here do not believe that in detached system you may have such a huge mass transfer rate, right? So I did the exercise. I said, okay, this is a cataclysmic variable where the secondary is filling its row slope, but in order for it to move this point to make it filling its row slope, I have to up the white dwarf mass to 0.85, 0.9, and low the mass of the secondary, and it's incredibly small mass. It's 0.45 solar masses. In such case, this will be it should be cooler a little bit later, K star, K3 or K4, in order to fill its row slope, and it should be hypothetically 0.45 solar masses star. So because the optical observations doesn't allow us to determine the spectral type of the secondary very precisely, I thought maybe an infrared observations will help. So we did the observations at the Grand Tecan telescope with the Emir spectrograph, and we did 8 nights observing the star about the same time. So we covered all the orbital phases. And here are the results. This is a preliminary. I am not very familiar with the infrared spectra. I talked to some guys who did infrared spectra of cataclysmic variables, and they basically said we couldn't learn much from infrared spectra. And that's true. I tried to fit this observed spectra with different type of stars from K2 to K4. I don't see much difference between them, or at least there is no enough difference to say this is later than earlier. You can see it's the same in the age band. I don't know if you see details here, but basically some lines, the difficulty of spectral classification also is because the infrared observations were made not in the minimum state where you see only K star. There is a contribution, some contribution from accretion even in infrared. So I cannot just measure equivalent weights of the lines and say this is K3 or this is K2. You go to the K band, it's the same. There are some lines, the sodium lines that doesn't fit K2, and they can be as late as K5. Although the sodium line can be some of it come from the interstellar medium or surroundings of the star, so that's not a good argument. So at the end of the day, after spending a lot of time looking at the spectra, I wake up in the morning saying, oh, it's later than K2, and then during the day I said, no, it's maybe K2. So my conclusions are there are no conclusions. I was not able to pinpoint the correct spectral type, and as you saw from the earlier figure that I showed you, there is a huge difference. It's K2 or it's K3. If it's K3 or it has 4,800 degrees, then it might be filling its row slope. If it's not, then it's probably not filling its row slope. But either way, if it's filling its row slope or not filling its row slope, we have problems, because if the system is detached, we have to explain how you form that huge accretion rate, I mean, the wind from a K star, okay, it's 10 minus 12, 10 minus something, if it's fast rotating, you can up it a little bit, but not to 10 to minus 9 solar masses a year. However, if it's filling its row slope and it's a CV in a sense already, then you have to explain how a star which 1.3, 1.4 solar radii, and with the mass which is less than the nuclei of a K-star should be 0.48 solar masses, has effective temperature of almost 5,000 or 48,000 degrees effective temperature. So I think looking at the solution of this dilemma, we can learn a lot about this. First, the influence of magnetic field on the evolution, as Diogo was telling in his talk, and then about some different, maybe different evolutionary track that brings the secondary star to these parameters, which I think do not acceptable with the standard evolutionary models of single stars. Thank you.
What are the evidence that you have an accretion or huge magnetic field? I couldn't get, maybe you have a just chromospherically active K-star.
Well, chromospherically active K-star would have, I mean, these emission lines appear and disappear.
Okay. Flares, no flares?
No, you cannot have flares every 29 days. I mean, I don't have direct evidence that there is a magnetic field. I tried to do the polarimetry, tried several things, but I cannot say this is the evidence that there is a magnetic field of the white. However, everything from presence of very high ionization lines, from X-ray, from modeling of X-ray, points that it works as a polar. It perfectly fits the polar description in every other sense. So now we are doing the polarimetry of this object in radio. Maybe we will come up with some answers.
So, Gagik, you may have been distracted in the last month or so, but there is a paper by Zhu et al. Have you seen this, which claims to explain your donor? It says it's Roche-Loeb filling and has an evolutionary model to get the right parameters.
Paper by who?
Zhu, XU, I don't know if that's Zhu et al., but it's on AstroPH.
Yes, I am familiar with that paper, and the reason I ask more questions than I give answers is that because a lot of people here present are expert on MESA evolution tracks. That's what they used to deduce their model, which doesn't explain how they found this solution or why this solution works. However, I started this considering that the secondary is a low mass, some strange star, after seeing their paper. Yeah.
Gagik, I think you have discovered a new kind of object, and it needs to be baptized. I would call it a bipolar system. But I have a question. I didn't quite understand if the emission lines that you see from time to time, it's an accretion disk, or it's just wind material that goes into emission. It's not clear to me.
Look at the profiles of the emission lines. They do not fit. They don't look like they are coming from the accretion disk.
Yeah, but you show a spectra with emission lines at the beginning.
But this is the profiles of these emission lines. And
okay.
they show two components. They are not like accretion disk lines that have, you know.
I wouldn't be surprised if, do you see chromospheric emission as well? Yes?
Yes, when the system is in the minimum, there is no emission lines, otherwise emission lines. We see calcium 2 and H alpha, very tiny lines.
Okay. So I wouldn't be surprised if the donor star has very low mass. If it is has evolved a lot and has lost a lot of mass during its evolution.
Maybe. I don't know why it is hot then. I'm not the chair. Sorry.
Okay, just a short question. Could you comment on periodicity of the signal? The periodicity, any variations of the signal? Is it 10 to the -9 mass transfer rate stable, or it's minus by order of magnitude larger, smaller?
If you give me an X-ray satellite to monitor this object, I will tell you.
Even though maybe not very expected theoretically, but do we have observational evidence that the binary is not eccentric?
Well, the radial velocity curve looks very sinusoidal and very precise.
Okay.
So you were mentioning the sodium line. You were mentioning the problems with the sodium line. Is it slightly stronger than you would expect? Is it this?
It is much stronger than K2 or even K3 should have. If I look at the sodium lines only, I would say there is a K5 star there, but otherwise it's not.
Maybe you answered this, but did you check the Gaia distance for this system?
Yes, 669 parsecs.
Right, but wouldn't it be too bright to be a CV, the secondary? So if I get the infrared magnitude of this thing at 600 parsec,
well,
it gives me like
this is where it should be. This is taking into account the distance.
Okay. Sorry, I missed that.
Are there any more questions? Let's take again.
Thank you.
Is this working? Yes. Well, I hope it will stay on. So I'm going to talk about a very special system because it's one of the rare systems which is double-lined binary system, double-line spectroscopic binary system, and for which the inclination angle can be determined very accurately, meaning that we can measure the masses of both components. However, doing so is not as straightforward as one might think, and which I hope will become clear in the course of my talk. So what made the system famous was the Nature paper by Santander Garcia, published in 2015, where they claimed that the system is composed of two equal mass pre-white dwarfs, consisting each of 0.88 solar masses, and this combined with the short orbital period of 4.2 hours would then lead to a supernovae 1A explosion. Here in this nice video made by David Jones, you can see it's an overcontact system, and you see here the flux of the system. It's changing when we see both hemispheres of both stars. We have the maximum flux, and then it decreases as one star moves in front of the other. And also the radial velocity curves change. The radial velocity curves were determined only with one line. This is this helium-2 line, which you can clearly see is double-lined. And to measure that, they use Gaussian profiles. This result was then later criticized by Garcia Berro et al., with I think the strongest criticism being that the luminosities and radii do not match up. So if we have, as they said in the Nature paper, system with a total luminosity of 1,000 times the solar luminosity, we would expect much lower masses. However, in defense of the Nature paper, I would like to say that these are single star tracks, and for example, if we would look at strip massive star tracks, then it would be no problem to have this high mass at such a low luminosity. while Garcia-Berro only carried out an additional light curve fit, showing that the light curves could be reproduced also with lower masses, we decided to do a more detailed analysis, combining an improved radial velocity measurement, as well as spectral fitting and light curve fitting. And yes, and so our first attempt was to use hydrogen-helium models to measure the radial velocities, and however, we did not find very good results with that, because first of all, our models did not fit the data very well. You can see that the helium-2 4686 is much stronger, the model, than the observation. And also we ended up with very different results looking at two different lines. Also we looked only at two different lines. So I decided to look at that in more detail, and also to find out why do we get different masses for the different lines. The first thing you might can think of is the wavelength calibrations, that there are some issues. And to check the wavelength calibration, I did the following. Namely, I looked at the nebula lines. Those are very annoying actually to do the spectral analysis, but are nice to check the wavelength calibration because those lines shouldn't change. And I used the same data as in the Nature paper, so the Osiris spectra. And I found that when I look at the different exposures, there are significant 0-point shift, which you can actually see by eye, so up to 54 kilometers per second. However, within an individual exposure, the wavelength calibration is surprisingly good. So at least up to H beta, it seems to be better than 5 kilometers per second. The red part is harder to tell because the nebula lines are quite weak and not clearly visible in all of the individual exposures. So it's possible that maybe in the red part it gets a little bit worse, and also that's nothing we can correct for. Then I applied this additional 0-point shifts to all of the spectra, and found that this cannot explain the different masses we get from the different lines. The next thing we thought was maybe it could be due to the red excess or cool companion reported by Rodriguez et al. And here in this plot you can see the blue line is the spectrum from Rodriguez as published in the paper. And when you look redwards of 5,000 angstrom, you might think that there is a red excess. However, it turned out that this is only a consequence of the reddening law used by Rodriguez et al. So they used the Cadelli reddening law, and when you apply the Fitzpatrick reddening law to the observation, which is now in black, then this red excess disappears. Also, I'd like to point out the Cadelli reddening law is considered as outdated. So it's also found that it overestimates the reddening in the SDSS bands up to 40%. So you please refrain from using this reddening law any longer. So this can obviously also then not explain a V-fitting procedure and the line profiles used. So obviously the pressure broadened lines in our system, a Gaussian is not a good assumption to make, and our hydrogen helium models did not provide a good fit to the data. So I wrote my own Voigt profile fitting program. And before I come to the results of that, I'd like to mention another possible error source, which is the blend with other lines. And here in this plot, I'm now showing the co-added Osiris spectrum. And when you look carefully, we can see lots of other absorption lines showing up in the spectrum. So we have our 4 helium-2 lines, 1, 2, 3, 1, 2, 3, 4, yes. And first I thought these are photospheric metals, and I thought, great, then we can derive metal abundances and have additional lines to use for the RV analysis. But no. What we have to keep in mind that this system is located at a very low galactic latitude, and what happens at low galactic latitudes is that you have a high reddening, as shown before, and when you have high reddenings, you get diffuse interstellar bands in your spectrum. So all these blue lines I'm showing here are diffuse interstellar bands. These diffuse interstellar bands, also called dips, they are thought to originate from complex molecules. It's not every dip is clear from which molecule it originates, but one example could be like fullerenes, which are like carbon onions. They look like soccer balls inside of each other. And when we now look again very carefully at that, is that we notice that some of our helium-2 lines are blended with these dips. So 4 of our helium-2 lines are blended with the dips. Only 1 of the lines is not blended with a dip. The thing about these dips is the equivalent width of them increases as the reddening increases. And here I'm showing a spectrum of a star which has a very similar reddening as Henize 2428. And so we can expect that the dips in our star are about the same than in this star. And here's the region around helium-4 5412. So the line also shown, used in the Nature paper to derive the masses, and they have very strong dips blended. And here in yellow I indicate the all the dips that blend with our line, because in our case the this helium-2 line is much broader. So, but since we can expect, okay, the equivalent lift should be about the same, we can now try to implement that in our RV fitting. And that's what I did. So again, I now using Voigt profiles, I did not make any assumption to the Voigt profiles before, other than requiring that they are absorption lines. And here I'm now showing the fit to the line also used in the Nature paper. And if I do not consider the dips, I do end up with very similar results. I still do get quite a high system velocity, which should be 0, because I shifted all the lines to be at the system velocity to 0, indicating that there still are some issues. And but now if I do include the diffuse interstellar band model, which you can see in green, the radial velocity amplitudes change quite a bit. So we do end up with a lower amplitude radial velocity curve, and one which has a higher radial velocity amplitudes. And also what you will notice is that the line profile now of the more massive one, with the smaller amplitude, has a stronger line than the one of the with the higher radial velocity amplitude. So the dips were required to have the same equivalent width as in the other star with the very similar reddening. And that I also did for helium-2 4686, which is also blended with dips. There the dips are not that strong, but still even such small dips can have a large impact on the radial velocity curves. So again, on the left without dips, the radial velocity measurements, and on the right with the diffuse interstellar bands. And again, the difference between the radial velocity curves becomes more extreme. And also, again, the lines are not equally strong, which can already be seen in the observation. So we have here much stronger line than in the other one. Now we come to the helium-2 4542 line, which is the actual interesting one, because that's the only one not blended with the dips. So that is one we should definitely rely on. And here I get, again, very different radial velocity amplitudes. So the smaller amplitude with amplitude of 136 kilometers per second, and the other one 225 kilometers per second, and the good system velocity close to 0. I also did this then for the fourth helium-2 line. It has a poor signal to noise. But the nice thing about this line is that we can actually see the diffuse interstellar band here in the observation. So we can model it, and I did that by using the coordinate spectrum and get then a nice, get a fit to this thing, and then included it in all of the fits. And if I do that, again, I end up with different radial velocity curves in both cases. Here in this case, actually, without the dip, the amplitudes are different. The difference between the amplitudes is much higher than in the one with the dip. But also, again, the system velocity very nicely close to 0, as it should be. And if we now compare this now with the result from the dip with the other helium-2 line, which is not blended with any dip, I thought I was really surprised by that. I do end up with very similar radial velocity amplitudes in both cases. And this, I think, is a very nice result. And now we can go on and look at the dynamical masses, which is obtained from that. So here on the left hand, the results from the fits excluding the dips, and then on the right hand side, the ones which do include the dips. And so for the line used in the Nature paper, if I exclude the dips, I do end up with very similar masses, which also agree within the error limits with the Nature result. So only using Voigt profiles instead of Gaussians does not change like too much for this particular line, but all the other lines here do not agree with that. They show more extreme mass ratios. And however, if I do, and also they are not consistent with each other, but if I do include the dips, I do end up with very similar results. And yeah, again, for these two helium-2 lines, very similar masses. So these are the two lines we should rely on, because for those we don't have blends with dips, or we can model the dip. And yeah, so the mass ratio, you can see down there, it's smaller than 1 now. And now we finally can look at what could be the outcome of the system, which I show here. This figure is taken from Shen 2015. And here is our the masses of the primary and secondary, and our results now suggest that it has not enough mass to trigger a supernovae 1A. However, it might potentially then lead to the formation of an Alcor star, or under certain circumstances also to this supernovae dot 1A and or formation of a IM-Coven system. And with that, I like to end up with the conclusions. I also did then some atmospheric parameter fit. So for that, I used the Voigt profiles from my RV fitting to disentangle the spectra or decompose them. I subtracted the dips and the Voigt profile from always the other star, and also calculated a slightly bigger grid, and I found that both stars have very similar temperatures. The surface gravities differ by about 0.5 dex, and also the more massive star, which is here on the left-hand side, is found to have higher helium abundance. And the errors quoted here are just fitting errors, but I wouldn't rely on them too much because the system, the models we use, we still neglect metals in the calculations. Also, we have a closed binary system with two very hot components. We do not consider in the radiative transfer the incoming radiation from the other star, and also do not include stellar rotation, which is really hard to determine from the helium-2 lines. So I would still be careful with those results. And then I'd like now to come to my conclusions, namely that the diffuse interstellar bands, or I think blends with lines in general, have a large impact on the radial velocities you measure, also the line profiles which you use, and of course then also on your atmospheric parameters and the dynamical masses. And our preliminary results suggest mass ratio below 1, and that the system will not end up as a supernovae 1A. And yeah, but we still have to do the light curve fitting again, but we do not expect that the inclination angle and these results will change much. And with that, I'd like to thank you for your attention. Yeah, but I think it's very hard to estimate what should be the rotational velocity of the system.
Well, it has to be a defined model with the photometry. A photometric model, it will tell you what the rotational broadening should be. It should be all together.
I will think about that.
Thanks. So, yeah, it's really great that you managed to make all of the lines agree now, but I wonder, a big problem that we have in all of these systems is that all of these lines are coincident with nebula lines, so you have a big problem when you're trying to subtract the nebula background, especially given that the expansion velocity of the nebula is 20 to 30 kilometers per second, so it can introduce spurious signals in lines where you have bright nebula lines. Do you have anything to say about how you did the nebula subtraction for the spectrum?
We used your spectra, your reduced spectra, and the helium-2 lines. They should not be blended with the nebula lines.
So the line that we didn't use, the line that we used, isn't blended, but the others might well still have over subtraction or under subtraction of the nebula lines there. So it's worth investigating and probably re-reducing the data.
Okay.
So your conclusion in your preliminary results, you say that the mass ratio is lower than 1. So was this the basis, is the basis of finding the semi-amplitudes different? Not 200
Yes, they are different, as I showed. Like here.
Okay, so this will be completely a different result from previous papers, no?
Yes, it is.
Okay.
So, dear participants, we're just having a little bit rest, and at 2 o'clock, who requested lunch? We're having lunch at the restaurant. We will show you where is it. Just we will help you reach there. At 2 o'clock, we're having lunch for 1 hour. Thank you.
And we will have a poster session tonight at the end of the regular talks. I invite all the poster presenters to prepare 2-3 minutes to present their results, so the public will know whom to ask when they are looking at the posters. Thank you.
Okay, so thanks very much to everyone for coming back from lunch on time, and thanks to the organisers for inviting me. So I'm going to try and give a little bit of an overview of post-common envelope planetary nebulae and what they can tell us about the common envelope phase in particular. So before I go into that, we have to get everyone on the same page, and we have to define what is a planetary nebula. So as we should all know from our undergraduate physics, when solar mass or low intermediate mass star ascends the AGB, it ejects its outer envelope in the form of a dense, slow-moving stellar wind, eventually exposing the core, which then evolves as a pre-white dwarf and ionizes the ejected envelope, we see as the planetary nebula. But that doesn't explain on its own how we get this nice fine rim shape, because if this is just produced by continuous mass loss, you should have a sort of diffuse cloud. So the standard model of how these things form is that as the pre-white dwarf core is exposed, it launches a much faster but much more tenuous stellar wind, and it's the interaction between these two winds, the much denser, much slower AGB wind, and the much faster, much more tenuous pre-white dwarf wind, which sweeps this material up into a fine shell so that it can be ionized. So, knowing that AGB stars are roughly spherical, how do we go from that model to planetary nebulae that look like this? Or even like this? And so this has been a problem for the community for a long time, and various things have been proposed to solve this problem. For example, if you have rapid rotation, you can impart some kind of axisymmetry or density contrast into one of those winds, which will then be amplified when you have the interaction. Turns out that that doesn't work, because in order to be rotating sufficiently rapidly to make sufficient density contrast in the wind, it would have to be breaking up on the main sequence. Magnetic fields were also considered, but it turns out that they're not strong enough for long enough, so they can only impart very small deviations from spherical symmetry. So we're left with binaries. And the clearest way to do that is with a common envelope. But before I move on to how a common envelope can affect the shape of a planetary nebula, I want to have a quick aside in that planetary nebulae are complex because we only have one viewing angle. So, for example, you might see a planetary nebula that looks like this, which looks exactly like the archetypal PN that I put up in the first slide, and think it's a sphere. But it turns out that it's actually a cylinder viewed end-on. And we can break this degeneracy by looking at kinematical information, because these are emission line objects. If you place your high-resolution long-slit spectrograph, or integral field even better, across the nebula, and look at the velocity profile in the single lines that this emits, you can then reconstruct the three-dimensional shape and recover that an object which looks spherical actually isn't spherical. So even the spheres aren't spheres when it comes to planetary nebulae. So we have something like 3,000 planetary nebulae in the galaxy, some 80% of which show clear deviations from sphericity, and even some of the remaining 20% might not be spheres because they might just be cylinders viewed pole on. So 80% of 3,000 is definitely not 60, and we only have 60 post-common envelope planetary nebulae. So how can the common envelope be responsible for imparting all of the density asphericities that we see in order to see aspherical planetary nebulae? Well, it turns out that finding post-common envelope binaries in planetary nebulae is difficult. The vast majority of the ones that we know on the previous slide were discovered by photometric variability. And in most cases, what we're looking at is an irradiation effect. So if you have a white dwarf and a main sequence companion, depending on the viewing angle, you will see more or less flux. If you are looking at the binary at this phase, you're seeing the non-irradiated hemisphere of the companion. If you see it at this phase, you're seeing the irradiated hemisphere of the companion. And so you have a sinusoidal variation throughout the orbit. And indeed, that's exactly what you see. Obviously, if you get lucky and the inclination is high enough, you might see some eclipses. But because we're looking at small pre-white dwarfs and small companions, it has to be relatively high inclinations. And in fact, we also have another bias in that we're only really sensitive to big secondaries, high inclinations, and short periods. So, as a sort of indication of the detection limit, I put a red line across this plot at 0.1 magnitudes of amplitude in this irradiation effect, which is more or less the lowest amplitude that was detected by the Diogo survey, which is responsible for the vast majority of the post-common envelope planetary nebula central stars that we know. So you can see that as we go to very late type secondaries, we would miss them because they're too small to have a notable irradiation effect. When we go to very low inclinations, the irradiation effect disappears because we're basically seeing constant amounts of the heated hemisphere and the non-heated hemisphere. And at much wider separations or longer periods, basically the amount of irradiant flux is too small. So, from a survey of the galactic bulge, the photometrically detectable post-common envelope binary fraction comes out at around 20%. But again, with this limit, this caveat, that really we're only looking at the systems that are earlier than mid-M type, periods shorter than a few days, and high inclinations. If you go and use other methodologies which are sensitive beyond this, for example, radial velocities or infrared excessors, then this can go up to maybe 80%, but with caveats that we don't know whether they're post-common envelope, much wider, and also susceptible to other effects. So it seems to all tie up. Maybe 80% of planetary nebulae are binaries. So maybe we've solved the problem from the PN point of view. What can PN then tell us about the common envelope? So the best thing that we can do is then study these individual objects in detail and try and look at their own evolution. So the way to do that, by simultaneous modeling of photometry and radial velocities. And here you have an example of one such system and an example of some of the problems that we run into with these, in that you have a very bright nebula. So if you want to do multicolor broadband photometry in order to get good handles on the temperatures, you have to deal with this huge blob contaminating all of your photometry. Unless you're willing to go to silly bands like H-beta continuum. But in any case, from that you'll be able to derive some of the parameters of the binaries, including their inclinations, masses, temperatures, this kind of thing. And so the first check that you might do is, considering that you expect the common envelope to be ejected in the orbital plane, primarily, this should impart a symmetry axis in the final nebula. And so the symmetry axis of the final nebula should always be perpendicular to the binary orbital plane. So in the handful of cases in which we've been able to measure independently the inclination of the binary from combined photometry and radial velocity modeling, and the inclination of the nebula from the spatiokinematic modeling that I showed you earlier on, you find that there's a perfect one-to-one relation. And it turns out if you do the statistics of this, to find that kind of chance alignment is 1 in a million. So it's pretty clear that we've proven that the common envelope really is doing the shaping of these systems. Beyond that, you can look at the parameters of the stars themselves. When you look at the main sequence companions in these systems, every one of the main sequence companions which has been subjected to detailed photometric and radio velocity monitoring comes out to be inflated, and not by a factor of 7%, but by a factor of 2 or 3. Hugely inflated. And so we take this as an indication, and I'll show you more evidence of why we take this, that before the common envelope, there is a period of relatively intense but short-lived mass transfer, which knocks the secondary out of thermal equilibrium. But before I do that, you can see I put a little asterisk on every, because there's one caveat, there's one system that we discovered earlier this year, where the secondary is not inflated at all, but it's Roche-Loeb filling, so it can't be inflated. And it turns out that if you think both stars here are essentially Roche-Loeb filling, as the pre-white dwarf star evolves and shrinks, continues to shrink, there's a fair chance that we will begin to see mass transfer backwards onto the primary from the companion. And we even have a system that we've seen before undergo a nova eruption while the PN was still there. So this could be a system to look out for which could explode as a nova. So more evidence of why we expect this mass transfer to happen before the common envelope. We go back to this object, Fleming 1, which you can see shows these pairs of jets which have a clear precession in them. If you compare the precession period that you derive from these jets to what you would expect from hydrodynamic models, you can see that the period that they would predict is something like 100 to 1,000 years, whereas the actual current orbit, the post-common envelope orbit, is 1.2 days. And so this clearly traces an episode of mass transfer which must have come before the common envelope phase, when the period was as long, perhaps as long as 100 years. And in fact, you can also look at the kinematical ages. Basically, if you look at how fast these things are moving and wind the clock back, and you see that in several of these systems, these polar knots or polar jets are older by a few thousand years than the central parts of the nebulae. So again, a strong indication that these polar ejections are the consequence of pre-common envelope mass transfer. Yet more evidence of this mass transfer. In the central star of the necklace, Michalski et al. Found that the very low mass companion, which is a subdwarf, is actually heavily enriched in carbon, clearly as a consequence of mass transfer from the carbon-enriched primary. Okay, so that's a lot of individual systems. What about in general? So in general, while we have relatively small number statistics, the period distribution is consistent with the general white dwarf main sequence population. So it's a strong indication that we're not looking at unique cases. These are the precursors of all white dwarf main sequence stars. And then looking at the population as a whole, you see that we find something like 20% of all of the ones that we've discovered are double degenerates, which is extremely high when you take into account that double degenerates should be much more difficult to find, because you need to have them at very short periods in order to be able to see photometric variability, and also and also there are several systems which are consistent with being post-RGB systems, which again is interesting because if you understand the radius evolution of a solar mass star, basically the difference in maximum radius between the RGB and the AGB is very small. So most lower mass stars should experience a common envelope while on the RGB, if they are to experience a common envelope at all. And there are big questions over whether these stars would be able to survive a common envelope without merging, because you have a more massive envelope and a more bound envelope. But it seems as though these systems do indeed exist and do indeed survive. On top of that, almost all of the companions that we've found are late type, K or M stars, nothing earlier than that other than one strange system. This, even though it's very small number statistics, is probably consistent with the picture that we have of the common envelope that was mentioned earlier this morning, that you need a relatively high mass ratio before the common envelope in order to experience unstable Roche-Loeb overflow and plunge into a common envelope. So I've talked about the stars, I've talked a little bit about the morphologies of the nebulae. Now I want to go into something completely different, which might not be known to anybody in the room, and talk about the abundance patterns in the nebulae themselves. So there is a very long-standing problem in all of nebular astrophysics, not just in planetary nebulae, in that depending on the lines that you use to derive your chemical abundances, if they are derived from collisionally excited lines or recombination lines, you can derive very different abundances. And this is found across all astrophysical nebulae, from novae, planetary nebulae, H2 regions. And this is a big problem because in general, most of these nebulae are so faint that we only use one form of these lines to measure the abundances. So for example, if you're mapping the abundances of a galaxy, you will almost always do it with brighter collisionally excited lines. And if you have this huge discrepancy between recombination lines and collisionally excited lines, how are you certain that you're measuring the right abundances? And so it turns out that for the galactic population of planetary nebulae in H2 regions, you have this kind of distribution in the discrepancy between these two methods. So basically this is the ratio of abundances using these different lines. And you can see that it's more or less a normal distribution around maybe 2, but with this very long, very tall tail at very high discrepancies going up to almost 1,000. If you then plot which ones of these are planetary nebulae, and in particular which have binary central stars, you can see that the binary central stars, the PN with binary central stars, all cluster at the very high abundance discrepancy side. Meaning that in these systems, if you derive the abundances using recombination lines, you have abundance which is a factor of 100 higher than just from the collisionally excited lines. So what does this mean? We also see that there might be a correlation with the period, the post-common envelope period of these stars, in that beyond a day or so, we no longer see this huge discrepancy. We see some discrepancy, but certainly not factors of 100. If you actually image these recombination lines and collisionally excited lines, which should be coming from the same gas, so these are lines from the same chemical species, doubly ionized oxygen, and yet you see that the recombination line has a much different structure to the collisionally excited line. The collisionally excited line is more extended, and the recombination line is much more central. This is a fairly strong indication that in fact the nebula has two different components. It has a normal component of around 10,000 Kelvin and more or less solar metallicity, which makes the outer nebula, and then you can reproduce this kind of structure if you then have another phase of gas ejected into the nebula with a much higher metallicity, which then cools much more rapidly and has a much lower temperature. And that's what makes it brighter in the recombination lines. And in fact, we see this sort of ubiquitously. So this is unpublished Muse data of several objects blinking between these two emission lines. And you can see in every case, the recombination line emission is always more centrally concentrated. So the recombination line, which is tracing this higher metallicity gas, is always more centrally concentrated. So this makes you think perhaps there might be some form of eruption. If you have a higher metallicity gas appearing closer to your central star, perhaps at the end of the common envelope, there is some sort of event which ejects reprocessed material. And it actually turns out that if you look at the abundances, the abundance patterns, rather than just being higher metallicity, if you look at the individual abundance patterns, they are very similar to neon novae. And if you look at the masses, the ionized masses in these objects, they're also very compatible with novae. So exactly how do you make that fit with the picture of the common envelope? Does it mean that the common envelope only terminates when you have some kind of reprocessing event? Perhaps when there's some mass transfer backwards, because as we may know, the majority of hydrodynamic models of the common envelope fail to eject the majority of the envelope, only managing to lift it from the central binary, so perhaps there's fallback. In any case, it's definitely more complicated than we might be led to believe just from having some kind of alpha prescription. So, I think I will leave it there and just say that it's become clear over the recent years that binaries, particular close binaries, but also what I haven't mentioned here, because we're talking about compact objects, compact white dwarf binaries, is that wide binaries also play a significant role, such that perhaps even the majority of PN are shaped by binary interactions. There's very strong evidence that the CE is a very complicated event where there's significant mass transfer before and perhaps some form of eruptive reprocessing right at the end. And given that these objects are the direct descendants of the common envelope phase and the direct precursors of the majority of the objects that we're interested in this room, they're very important tools for studying or complicating the picture of how these objects form. And if you're interested in more, you can feel free to read the book that we've just written on the topic. Thanks.
Thank you, David. Any questions?
The forbidden line and the allowed line, they are characterized, they have different, they are formed in regions of different densities. So this can also explain the different regions in which you see.
Yeah, so there are multiple possible explanations for this, which have been considered, including temperature variations, density, and chemical inhomogeneities. And it's now clear that in these extreme cases, that density variations and temperature variations don't match. So if you want to try and explain, these systems here, then temperature variations, in particular, do an excellent job. By the time you get up here, the level of variation that you need in temperature and density is so huge that it's just not possible. You really need chemical inhomogeneities. I would say not very much, right? Because we're pretty limited in terms of what we can actually see in these things. Mainly limited by the fact that everything is complicated by having the nebula there. So if you want to get very deep spectra to be able to look at the remaining envelope of the primary, you're always going to be complicated by the contamination of the nebula. So it makes deriving any kind of accurate parameters for this stuff is very difficult, and even in terms of looking at, for example, the masses. If you want to derive the masses of both the primary and the secondary, you're relying on radial velocity curves. In some cases, we get lucky and we get double-lined radial velocity curves, but most of the time when we have that, the lines from the secondary come from the irradiated hemisphere, and we don't have very good models of exactly where those irradiated lines originate from. So there's some small ambiguity in the masses based on that too.
Can you tell us something about the duration of the common envelope from these observations?
So there are people that have looked at the central stars with possible outer companions to see if you can determine how long ago the phase happened and how long it happened. Haggai Peretz has been looking at this. And basically the limits are very, very vague. And so from our side, the only real limits that we can put are that it must happen somewhere between the launching of the jets, which comes from pre-common envelope mass transfer, and the ejection of the envelope itself. So we can put an upper limit of about 1,000 years, but that's a strong upper limit. It's much, much lower than that. Beyond that, not really.
Is there any kind of difference in nebula shape abundances, anything between the double degenerate central stars and the single degenerate?
So we don't have anything particularly strong there, but there is, from some of the work that we're just doing now, looking at the ionized masses in these things, it seems as though perhaps the double degenerates have more massive PN. But that's really, again, very complicated, because for a typical PN, I don't know, typical PN, you measure the ionized mass that's in this annulus, for example, but there will actually be a huge, very faint ionized halo, which, depending on how much material is in there, it's very difficult to measure. You might be missing a huge fraction of the mass. The idea is that perhaps with the common envelope, you're not missing too much of that mass, because it should be ejected almost at once, but it depends when the common envelope happens. If it happens right at the tip of the AGB, then you will have all of the previous AGB mass loss, which extends much further out and which is missed by these typical measurements of ionized mass. So it's a possible relationship, which Miguel Santander Garcia is working on, but I wouldn't trust anything yet.
Last question again.
I have a similar question. Those jets that you showed and every interesting pre-common envelope development, if I understand correctly, it should only happen in a second common envelope, or in a double degenerate, or how you call it.
So, in fact, of the systems, so this system, for example, is a double degenerate. But then we also have systems which are not double degenerate, so all of these three are white dwarf main sequence, and one double degenerate, and it seems that it's not discriminate, but it should be from the most recent event.
Okay, thank you.
All right, let's thank David for everything.
I think it would be easier, if that's okay. Unless you have video.
Thank you. All right, and for our last talk of the day, before we go to the poster presentation, we have Todd Hillwig talking about compact double white dwarf population.
Thank you. So Dave made my job a whole lot easier by giving you a very nice introduction to all of this, so I don't have to review much of that. So one of the goals of studying these central stars of planetary nebulae and looking for binaries is, of course, to understand planetary nebulae and the common envelope and the ejection, but there are other benefits there. For example, central stars are generally brighter than typical white dwarfs because they haven't yet reached the white dwarf cooling track. The central stars are easier to find because there's a big glowing sign around them called the nebula. But also, when we think about these things, they are straight out of the common envelope. So what we get by looking at binary central stars is something that gives us birth rates for these types of objects, gives us initial distributions for orbital periods, masses, binary fractions. So in that way, we can start looking at these as a different kind of sample than field white dwarf binary systems. So to that end, a number of us, Dave, certainly Brent Mizalski, Howard Bond, sort of started all of this in a large way. We've been looking for these types of systems for several decades now, trying to build up a sample. Dave pointed out the sample of about 60. George Jacoby and Ursula DeMarco and I have data from the K2, the Campaign 11 field, that includes about another 20 to 25 binaries on top of that, which we haven't confirmed entirely yet, but are in the process. So using that sample, it's now starting to get large enough that we can start to say something a little bit bigger. So this is work that is currently underway. These are fairly preliminary results, but I've been working on some Monte Carlo simulations of these distributions to try to figure out what the larger sample might be able to tell us. So looking at the orbital periods, the hatched region there are the observed central stars. The green is the model that I've used. It's a log normal distribution. And I'm focusing now on double white dwarfs at this point. This is the distribution for all binaries, including main sequence companions. Here are the double white dwarfs that we know of. These are not all entirely confirmed. The ones that are not confirmed have ellipsoidal variability as the primary photometric variability. Really, the only way to get that in these systems is if it's a double white dwarf. If there is a main sequence companion there, then any radiation effect is going to dominate excuse me, over any ellipsoidal effect. So, in addition to using the orbital period distributions, I've assumed some mass distributions. I've explored some different ones, so a bit of a complicated plot here, but the bluish color there are central star masses. That's a 3 Gaussian fit from Kepler's paper in 2007 of DSS sample. I've removed the high mass component, so he has 4 Gaussians, one of which was a high mass component at just over 1 solar mass, centered there. I've removed that, assuming at this point that those are essentially mergers, and that those high mass objects are the result of merged binaries. And the companion masses are one of the things that I've been trying to explore in this process, and what's here is a single example of that. This is a probability distribution for the mass ratios that goes as the mass ratio to the -7. So very, very strong. Anything less than about -5 simply doesn't work with the distributions that we see. We don't have large samples. The error bars here actually show ranges for the 8 published double degenerate central stars. So the reddish lines are for the central star itself, and the black lines are for the companion. And they are at least consistent with these. I certainly can't say that they point to these distributions, but they are consistent. And also the companion, in all of these systems, I've assumed that the companion is more massive than the central star. It may not always be the case, but made that assumption here as a beginning. The inclination, thinking about the solid angle of the axis and how that works, there will be more high inclination systems that we'll see. So the probability distribution there goes as the cosine of the inclination. And for the ages, I've just chosen a flat distribution from 0 to 50,000 years. If anyone wants to tell me exactly how old planetary nebulae can be, I would love to hear that. If you look at ages across the literature over the last 30 or 40 years, you can find everything from 10,000 to 100,000 years. I've sort of chosen 50,000 years. The complication here comes in when we decide what 0 means. And Dave alluded to some of this in his talk. The issue here being that when I started running these samples, every time you get a close binary as a result of common envelope evolution, the separation of the 2 stars is smaller than the central star should be if we use the evolutionary tracks. So we know that some of that is simply stripped away in the common envelope. What would have been in the single star models, some mass that would have been there, is now no longer there. It has to have been stripped away by the binary. So I simply set age 0 as the time when the radius of the central star is equal to the volume radius of the Roche lobe in the binary system, and evolved it from there using tracks from Hall and Miller-Bertolini. So I essentially went in, randomly selected from those distributions, came up with a sample, and started doing some calculations from those. So using those tracks could get the Roche lobe filling factor of the companion star and of the main sequence star, depending on the age, or sorry, the central star and the companion, both double white dwarf system here. And the main reason for this, and really what started me down this path, is that, as Dave mentioned, most of the variability we see from these are from main sequence stars where you get interradiation effect. And about a quarter of all of the photometric variability we see, though, is from an ellipsoidal effect. Well, as the central star evolves and shrinks, it pulls away from the Roche lobe, so we shouldn't see the ellipsoidal variability for very long, and I wanted to figure out sort of what fraction we might be seeing. So how many of these systems are actually showing an ellipsoidal effect? And based on these, about 26 to 30% show an observable ellipsoidal effect. So if we have about a quarter of all of our observed close binaries as double white dwarfs, and from a sample that I've been working on with a number of collaborators, we found a binary fraction or observable photometric variability fraction of about 15% in these systems. So it works out that 10 to 17% of all planetary nebulae should have a double white dwarf central star. If we calculate the merger times for the binaries that come out of this Monte Carlo simulation, then about 55% of that sample have merger times less than about 10 billion years. And using a very rough approximation for supernova 1A progenitors, just assuming the total mass of the two is greater than the Chandrasekhar mass, and a merger time of less than 10 gigayears, 12 to 15% of the sample of double white dwarfs. That means that around 1 to 2.5 or even 3% of all central stars should be supernova 1A progenitors based on this sample, which seems relatively high. I was a little surprised by that. So I went through and used this sample to actually evolve a stellar system to see what kinds of numbers those would result in of an actual observed sample. So remember, all of that, those were birth rates and initial distributions for when these systems are created. And over time, of course, you build up, you lose some to mergers, and you continue to build up single white dwarfs. So evolving this, assuming a star formation burst at about 2.4 gigayears to match some of Mayaw's and others' papers, assuming a constant white dwarf formation rate, and also a constant stellar mass in the system of 15 to 20 solar masses in stars for every white dwarf, also assuming a double white dwarf fraction of 12%, and then randomly selecting stars from that Monte Carlo sample that I created. And these results, it turns out, are most dependent on the central star mass and the companion mass distribution. So this is one area where I've begun to try to sample those types of distributions and see what works and what doesn't. So the current supernova 1A rate then, based on this, so evolving this from about 2.4 billion years to the present, we get around 0.5 to 1 times 10 to the minus 13 supernovae 1A per year per solar mass. Measured rates for Milky Way type galaxies are around 1 times 10 to the minus 13. So very much in keeping with the expected rates. Current white dwarf mass distribution, so these are binaries that merged, have merged already, and have a total mass less than the Chandrasekhar mass. A little hard to see, but the purple down there at the bottom are those merged masses. This is assuming that all of the mass is retained, none of it is lost. So this would be an overestimate in the total amount of mass, and it is in fact slightly higher than we see in, for example, Kepler's SDSS sample from 2007, but it is consistent with that. And we see about 2 to 3% of all white dwarfs would be these merger products at high masses. And then finally, calculating a delay time distribution from this sample. The open circles are the result of my work. The filled points are primarily from Dan and others, taken from observations. The solid black line with the blue around it is from field galaxies from 2017. And the lines are all from theory, primarily population synthesis calculations. And again, this is one sample. This is really the best fit kind of sample for the delay time distributions. But we see a turnover there at small delay times that is consistent with the shape, primarily the shape of the theory, but not quite consistent with the observations. So it would seem that if double white dwarfs are primarily responsible for type 1a supernovae, that there is some other contribution that occurs, but primarily at short delay times. So quick summary from the Monte Carlo simulations that I've run, and then the follow-up. Using central stars is a pretty powerful way to begin looking at this because they are really providing the birth rates for double white dwarf binaries and initial distributions for periods and masses. 10 to 17% of all central stars based on this we expect would be compact double white dwarf binaries, and somewhere between 1 and 3% approximately of all central stars would be type 1a progenitors. And then depending, again, on the distributions of central star mass and companion masses, it's possible that these could produce most of the observed type 1a supernovae. And the delay time distribution demonstrates that, but then also shows that perhaps there's an additional source at shorter delay times. Something like the core degenerate scenario, for example, is one option. That's it. Thank you.
Any questions? Yeah.
Just a general question. When you calculate a merger and in general talking about massive white dwarfs, what about neutron production? Because in case of merger, the temperatures are very high, so it's very good conditions for nucleus capture electrons, decrease the number of electrons. So do we really reach the Chandrasekhar limit in this case, or it might be the collapse of white dwarf cellular stage?
Yeah, and I just have not gone there at this point. So it's possible that we might be able to say something from this sample, but right now, haven't looked at it, but I will think about that.
If the lifetimes are as uncertain, the lifetimes of the planetary nebula is uncertain, as you say, I'm wondering exactly how one gets the birth rates. Maybe I missed that. But if you can't, if it's a factor of 10 uncertainty on the...
Yeah, it does affect the birth rate, and I've tried taking into account some of those here. With the evolution of the sample, it ends up having a little bit less of an effect. It would affect the ellipsoidal variability a little bit more, simply because we would expect that if the age is longer, by the time they're 50,000 years old, none of them show ellipsoidal variability, really. So if you go to older times, then that percentage drops pretty quickly. If you shorten it, it drops a little bit, but you have to go way down. And really, we see planetary nebulae that are pretty clearly well older than 10,000 years. So I really don't think it's as short as that. The big question is it much longer than 50? And that would have a significant effect.
Another question? Over there.
I think it's complicated. The PN lifetime question is complicated because it's a function of a lot of things. It's a function of the expansion and density of the envelope and of the the brightness or the luminosity and temperature of the central star, because you have to have a dense enough nebula for it to be visible and a hot enough central star to ionize it. And so that depends a lot on the initial and final parameters of the system. So there's really no one-size-fits-all age that you can use for this.
Yeah, that's sort of why I went with 50,000 years, because certainly there will be differences, but as an average, it seems to work out reasonably well from ages that are listed in the literature.
Any other question? Okay, if not, let's start.
The idea is that the people who have posters presented here have a couple of minutes to say a couple of words about their posters, to present themselves, and free format, just don't exceed time limit of several minutes. Thank you very much. You can show something if you want.
Yeah? Okay.
Okay, so my poster is on a special kind of white dwarfs, and those are so amongst the hottest white dwarfs, so which have temperatures above 60,000 Kelvin roundabout. So lots of these objects show very weird absorption features, which are identified as ultra-high excitation absorption lines from, for example, oxygen 8. And the fraction of hot white dwarfs affected by that is very significant. So we expect at least 10% of all stars will show at some point in their evolution these lines. But it's not very clear where do they come from. I made some investigations and found from light curves from different surveys that most of these, so 80% of these objects show short periods from a few hours to days with amplitudes of 0.1 to 0.3 magnitudes. So it could be indicating the rotational period of the star, or it could also be that they are post-common envelope binaries. One model to explain the occurrence of these lines is that they stem from a shock-heated co-rotating magnetosphere, where the material is heated up by magnetically confined wind shocks to these high temperatures. However, for other stars, we found indications that they might be indeed close binary systems. For example, one system we found which shows like a reflection effect, so the amplitudes in the I and Z band are bigger than in the blue bands. And if you want to find out more, talk to me.
Thank you. Yeah, so,
okay, thank you. Hi, I'm Dave Salmon from Sheffield. My post is about trying to explain one of the anomalies in CV evolution. This is an orbital period versus just a number of systems at each orbital period. And we'd expect to find predominantly dwarf novae in the short period system, where only gravitational radiation is working, and predominantly nova-like to this end of the distribution. In fact, we find quite a, sorry, the pink colours are the dwarf novae, the white colours are the nova-likes. But we actually find them coexisting at the same orbital period. That's been a long outstanding problem for CV theory. And if I can just quickly jump across to this one. This is a graphic describing Mike Schara's hibernation theory. If I go to full screen, I'll put my specs on, shall I be quicker? So we expect, after a nova event, that the white dwarf remains hot, and the system would appear as a nova-like. Eventually the white dwarf cools down to dwarf nova mass transfer rates, possibly even ceasing mass transfer, going into hibernation, so it goes out of view. As the system, as the angular momentum losses build up, the system will recontact with its Roche lobe and eventually build up hydrogen on the white dwarf, and we have another nova, and it cycles around this circle, and hence you get CVs at the same orbital period, but with very different mass transfer rates. Mike himself found, I think it's about 4 nova shells around some dwarf novae, but in fact the best place to look for a nova shell would be around a nova-like, and that would then give quite a lot of support that this cycle does actually exist. So what we did was we went and looked at 56 nova-likes, and took deep H-alpha images, and we're searching for shells around them. If you want to know how many I found, you need to come over to my thing, and I'll tell you all about it. Okay, thank you.
Thank you. All
Okay, I am presenting a collaboration with Klaus Tappert, Maja Vukovic, and me from Universidad de Valparaíso. That's now Valparaíso, Chile, not Valparaíso, United States. And with Linda Schmidt-Obreich from ESO. What we did is something simple. We took, of course, Gaia DR2 and took all the information we could get from emission luminosities or emission fluxes of nova shells. Mainly this is a catalog of Downs and Dürbeck 2001. We calculated again the distances. Then we calculated luminosities and versus time. So we get diagrams, log luminosity of shell versus log T in a between a few days after nova maximum to about several decades. We took the emission lines of H alpha and of O3 5007 forbidden line in these nova shells. Okay, what we found, and we make a grouping. The grouping first on the T3, that means between rapid and slow nova, as well as the grouping of Strope et al., which corresponds to different light curve types. And only a small part of the results are in our poster. The main conclusions are that the groupings give lower standard deviations than the T3 grouping. So it's easier to distinguish this way from the Strobe grouping the behavior. In general, we got always a behavior that between at the early state we get a more or less constant phase in luminosity. Then we got a typical slope going down, which the slope of O3 is steeper than the slope of H alpha. And we got also some indications of constant states well at the end, very, very decade, but only in some of these groups. So I invite to look at the poster, and if you have any questions, you are welcome to ask. Thank you very much.
Hello everyone. My name is Georgi Latev from Institute of Astronomy and National Astronomical Observatory, Bulgarian Academy of Sciences. And my poster is about rapid variability of the intermediate polar EA quarry. Okay, this is the part of the sections of the poster. This is the main characteristic of this star, and we can see the mass of components, white dwarfs and K components. And the most obvious photometric features is in optical light curve are separate or avalanches of flares. And in this study we examine some observational properties of the flares. And okay, and this is our telescopes we use for observations. Schmidt telescope at National Observatory 2, Cassegrain telescope at Astronomical Observatory Belgrade and Rožin, and Dao-Kirchhoff telescope at Andromeda Observatory near to capital of the Bulgaria, Sofia. We can see those all CCD cameras we used. All science images are about 20,000 in different band B, V, R, and E. And this is the standard, we apply standard reductions for bias, flat field, dark subtracted. In data analysis, for each observational session, we construct the light curves, separate these light curves by filters, and we calculate folded this light curve to obtain one single orbital phase curve for accuracy to measurements, the accuracy measurements of the amplitude, and the typical measures for rise time and fall time and amplitude. And this is the all data contracted in one orbital curve in V-band, and this is in additional, no in my poster, but we plan to examine this light curve in B-band. And this is the sum of results. Full amplitudes in the different bands are listed here, and the largest flare amplitude is observed at orbital phases. And okay, we try to see in any type of correlation between the duration of the flares in the amplitude, but this is the weak correlation. Okay, this is the orbital solution for in different bands, and this is the flares rise time distribution and the weak correlation between the amplitude and duration of flares. And this is additional. We try to detect any kind of QPSO in our query, and this is the preliminary results for this one. Thanks.
Right. So let's try to keep it a few just minutes so that everybody can go quickly. Yeah. So it's the poster. So.
Doesn't. Good afternoon, everyone. I would like to present a work which is connected with dynamo models for the accretion disks that are around white dwarfs. And so I would like to speak about the problem which is connected with magnetic field, which is very important to study the processes in accretion disks. And their generation can be connected with the dynamo mechanism, as in other astrophysical objects. And after that, if you use the dynamo models, you can take two ways. The first way is to describe some rough estimates, and the second way is to have a very hard code which will make necessary supercomputer calculations. It will be very hard to understand which has been detected, and the results will be very difficult to be described. And as for another areas of the dynamo theory, there is a model which is called the null-Z approximation, which allows us to describe the magnetic field in disk objects and to have a quite simple model which allows us to use not very hard numerical resources, and of course it gives very good results which are quite close to the realistic field, and so it will be important to have an approach for the accretion disk to use the same model and to describe the magnetic field in accretion disk using the same approximation. I with my co-author, we have described this magnetic field evolution using this model, and we have obtained that for different dynamo numbers that is constructed of the kinematic parameters of the accretion disk, you can have the magnetic field growth, or for some cases you can have its decay. Also, if we compare the results with the magnetic fields of galaxies, the critical number for the dynamo number is much lower, and so it is quite easier to generate the magnetic field in the accretion disk, neither in the galaxy. And so it's all, we can speak about it near my poster if you are interested in it.
Thank you.
Hello everyone, my name is Alexa Muthel and I'm an undergraduate researcher at Michigan State University. I work with Dr. Elias Eide and Dr. Laura Chomek there. So my work is a systematic study of novae that show hard X-ray emission, which were observed with the Swift X-ray telescope. With the detection of gamma rays from novae back in 2010 with the Fermi-Lat telescope, we realized that shock interactions are much more important in novae than previously thought. So we are trying to understand the connection between hard X-ray emission and gamma ray emission, as well as why only some novae show hard X-ray emission. And so far we have found that novae do not show hard X-ray emission and gamma ray emission at the same time. So if you'd like to learn more about my work, I invite you to come look at my poster. Thank you.
So continuing our work trying to find more binaries in planetary nebulae, we present two back on the poster back here, one in a confirmed planetary nebula that is in fact a double degenerate system, second in a possible planetary nebula, and we found it to be a radio velocity variable, and also Nicole doing some spectral modeling, it turns out to be an SDB star, and the evolutionary age of that would be 2 million years, and while I said we weren't quite sure what the ages of planetary nebulae are, they're not 2 million years. So probably not a PN, but it is an interesting binary with an SDB star.
Hi, I'm Mike Politano at Marquette University. I've been out of the research loop for about 4 years taking care of my mom and sister. So this is my way of rebooting things. The poster that I have is work from a undergraduate student of mine who's looking at an alternate way of trying to determine the final orbital separation in the common envelope phase. Energetically, you can use this common envelope prescription with alpha, but still you have to reduce the frictional torque enough so that the secondary will stop spiraling in. So he looked at flat mass radius profiles in the interior of AGB stars from 1 to 3 solar masses to try and determine where this regime would be. And if you want to learn more about that, please look at the poster. Thank you.
All right, thank you. So I think that's everybody that wants to share. Gagik has an announcement.
Yeah, I'm just wanting to say that this vino and cheese session will start shortly. We would like to hang around for a little bit until Boris returns from university and we celebrate the end of the first day. At least I will be celebrating that. Also, a small announcement. I noticed that at the Opera House, the other side, where is the Armenian Philharmonic Orchestra is usually playing, there is an interesting concert of Gata group. I'm sorry, I don't know if there are tickets available or no, but it's an interesting group that plays folk music. If you want to, a suggestion if you are looking to learn anything about tonight at 8. Thank you very much.